Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us to the very edge of everything we know, or perhaps to the strange realization that there is no edge at all. We'll explore whether our universe, this vast stage of stars and atoms, might actually be a hologram, a grand illusion encoded on a two-dimensional surface. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each of us in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let your thoughts slow down. If your mind begins to drift, that's perfectly fine. Let it wander like starlight across the dark. We'll still be here, quietly unfolding the story together. Let's start our journey not in space, but in the imagination of the 19th century, in a time when the universe was still a place of wonder, mystery, and elegant geometry. Picture a square, 4 equal sides resting neatly in 2 dimensions. Now imagine lifting its corners upward, letting it breathe into a cube. That 3rd dimension feels natural to us, a simple step upward into space. But if you were to take that cube and stretch each of its corners once more, this time into a direction that doesn't exist in ordinary space, one that's perpendicular to every direction we can point to, you would arrive at something called a tesseract, or hypercube. A 4-dimensional shadow of a shape we can't quite see. For mathematicians of the Victorian era, this was not just a thought experiment, it was an invitation to transcend. Bernhard Riemann, the German mathematician who first described new kinds of curved geometries, opened the door to a realm beyond the flat world of Euclid. He showed that space itself could bend, twist, and stretch, that triangles didn't have to add up neatly to 180 degrees. To a restless age on the cusp of modern science, this revelation was electric. The 4th dimension, invisible but conceivable, became a kind of frontier, a bridge between the known and the divine. In parlours lit by oil lamps and curiosity, Victorian thinkers spoke of the 4th dimension the way poets spoke of love, elusive, transformative, and possibly eternal. Some believed it was the hidden plane where the soul resided, the place we came from and would one day return to. Painters tried to capture it. Philosophers speculated endlessly, and spiritualists claimed to feel it brushing past their seances like a soft wind from another world. In those years, science and mysticism still danced closely, their hands almost touching. You can imagine the comfort of that idea, that beyond the visible world lies a gentle continuum, perhaps heaven itself. But as the century turned and curiosity deepened, another kind of imagination began to stir, darker, colder, more cosmic. For a writer named Howard Phillips Lovecraft, the 4th dimension was not a refuge of angels, but a labyrinth of incomprehensible geometry, filled with indifferent gods. In his stories, characters who glimpsed those higher dimensions didn't find enlightenment, they found madness. For them, the unknown wasn't a ladder toward transcendence, it was a mirror reflecting how small we truly are. And perhaps in a quiet way, Lovecraft's horror was only a different language for the same awe the Victorians felt. The same dizzying recognition that our senses are too small for reality. Whether we imagine divinity or darkness, the feeling is the same. The humbling awareness that beyond the edge of what we see, something vast awaits. It's easy to forget that both awe and fear are children of curiosity. The same impulse that drives a scientist to calculate or an artist to paint can also drive a poet to shudder. The more we try to understand the universe, the more we realize that understanding itself may be limited, that our minds, built to navigate days and distances, might never truly picture the infinite. Yet we keep trying. We keep reaching for that invisible direction, hoping to glimpse what lies beyond the cube, beyond the three familiar lines of width, height, and depth. We can't imagine it directly, but we can sense its presence, like a shadow cast by something just outside the room. Modern physics inherited that same yearning, but instead of looking for angels or monsters, it began to look for structure, for the quiet architecture beneath everything. Einstein, Planck, Hawking, Maldacena, each in their own time searched for a deeper layer hidden beneath the visible. And now, more than a century after Lovecraft's Trembling Stories, science has returned to the question of higher dimensions, not as superstition, but as an essential key to reality itself. But here's where it becomes wonderfully strange. Instead of discovering that the universe is made of countless stacked dimensions, some physicists suspect the opposite. That all of our three-dimensional experience, the distances, the planets, the galaxies, even our sense of volume, might be nothing more than a grand projection, a three-dimensional image emerging from a two-dimensional surface at the edge of space, a cosmic hologram. If that sounds too abstract, think of it like a film projected on a screen. The picture looks deep, filled with mountains and shadows and stars, but the real information, the actual code, lives on the surface of the film. Every detail of that deep-breathing world is written flat, and when light passes through it, the illusion of depth is born. Our universe, some say, could work the same way. Everything we see might be the echo of information written on a distant boundary, a place we can't reach, but that quietly defines every atom, every heartbeat, every thought. It's an idea both beautiful and unsettling, that the edge of the universe is not a wall, but a whisper, that we're not inside space, but rather on it, like shadows of something more fundamental. And if that's true, then the search for the cosmos's edge isn't about distance at all. It's about understanding how reality stores its own memory. In the quiet corners of science, this idea is known as the holographic principle. But before we can understand how the universe might behave like a hologram, we need to trace the path that led us there, from steam engines and entropy to black holes and information. Because, in one of the most poetic twists of physics, the story of the universe's edge begins not in the heavens, but in the heat of human invention. And so, our quiet exploration now turns to the 19th century once again, to the flicker of coal furnaces and the hum of pistons, where a young engineer named Sadi Carnot began to ask how energy moves, and how perfection, no matter how carefully designed, always seems to slip away. In the quiet light of the next idea, something darker begins to stir beneath the Victorian dream. For every age that worships order and symmetry, there comes another that trembles at the chaos beneath. The 19th century had its poets of progress, mathematicians who tamed geometry, engineers who bent steam to their will. But it also had its prophets of dread, whispering that knowledge might open doors best left closed. One of them was Howard Phillips Lovecraft. Born in 1890 in New England, Lovecraft was a man haunted by logic. He loved astronomy and physics, and yet his imagination twisted those wonders into nightmares. In his stories, knowledge was not light but exposure, a flood so bright that it blinded. When his characters encountered higher dimensions or alien geometries, they didn't gain enlightenment, they lost themselves. The universe, he warned, is not built for human comfort. It is vast, cold, and serenely indifferent. In The Dreams in the Witch House, one of his strangest tales, a student named Walter Gilman rents a small room near the university. The walls are crooked, the angles slightly wrong, as though the room itself refuses to obey the ordinary geometry of the world. At night, he dreams of planes of space folding over each other, of creatures that move sideways through dimensions that human eyes can't follow. The more Gilman studies these shapes, what he calls non-Euclidean calculus, the less he understands. His curiosity becomes an infection, and in the end, the very room he rented devours him, as though reality had grown tired of being questioned. Lovecraft's horror was not about monsters in the dark. It was about the dark inside the mind, the moment when comprehension fails. In that failure, he found something cosmic, a truth too large for language. His stories weren't really about demons. They were about the limits of reason, the same limits that scientists encounter when equations grow too strange to picture. And in a strange way, Lovecraft's fiction anticipated the psychological side of discovery. Even today, when physicists talk about multiverses or quantum entanglement, there's a similar unease, a quiet echo of his dread. Not fear of ghosts, but fear of scale, fear of infinity itself. Imagine looking up at the night sky, where the stars spill like powdered light. You can trace constellations, count galaxies, even estimate their distances. But when you realise that every point of light is itself a sun surrounded by possible worlds, and that this goes on and on and on, something inside you shifts. It's not terror in the ordinary sense, it's a soft panic, the kind that arrives when your mind brushes against the infinite. Lovecraft gave that panic a voice. He wrote of humans as cosmic dust, fragile beings, pretending to be central. And though his tone was grim, the insight was not so different from that of science. That scale humbles us. Our eyes can only see a fraction, our instruments only reach so far, and yet we keep reaching. In his lifetime, the idea of higher dimensions still belonged mostly to mathematics. People could draw diagrams of a cube turning into a tesseract, or describe a four-dimensional shadow, but they could not imagine what it would feel like. Lovecraft filled that gap with emotion, the vertigo of realizing that the universe may not care whether we understand it. He turned abstraction into sensation. The unease he described is the same feeling many scientists quietly admit to when facing equations that stretch beyond their intuition. And perhaps this is why his stories still resonate. They are reminders that curiosity is never safe. Every time we open a new door in physics, the hallway grows longer. The equations we thought would tidy the universe instead reveal deeper questions. What is energy? What is space? Why does time move forward at all? The deeper we dig, the more we suspect that reality might not just be strange, it might be stranger than we can ever know. Yet, there is beauty in that strangeness. The same terror that haunted Lovecraft has become a kind of modern awe. When we talk about black holes bending space-time, or the quantum fields humming invisibly beneath matter, we are, in a sense, walking through Lovecraft's crooked room, except we no longer see it as cursed. We see it as the architecture of creation itself. To understand that transformation, think of standing on the shore at night. The ocean stretches into darkness, its surface glinting under starlight. You can't see the end of it, but you know it's there, curving gently beyond the horizon. The unknown is no longer an enemy, it's a promise. That is how science differs from horror, not by denying the fear, but by learning to live with it. Where Lovecraft saw insanity, physicists see opportunity. Where he imagined monstrous deities beyond the veil, we imagine elegant patterns waiting to be found. Both begin with the same feeling, the shiver that comes when the human mind touches something larger than itself. Even now, when physicists describe the universe as possibly being two-dimensional, a cosmic hologram where depth is an illusion, the idea sounds like a Lovecraftian revelation. Yet we greet it not with screams, but with wonder. We no longer fear that the cosmos will consume us for looking too closely. Instead, we marvel that we are capable of looking at all. Perhaps that is the secret Lovecraft never saw. The horror of the infinite and the peace of the infinite are made of the same material. They depend only on how gently you gaze into it. To one mind, it's an abyss. To another, it's a quiet mirror. And so, as we drift further into this story, we carry both perspectives. The fear that knowledge can unmake us, and the faith that it can also set us free. The universe has room for both feelings, for the trembling of the hand that draws the first line, and for the calm that comes when we see the pattern complete. Ahead of us lies the first true step toward understanding that pattern, a journey from imagination to mathematics, from superstition to the laws of heat and motion. If we follow the thread a little further, the crooked geometry of dreams will lead us into the measured rhythm of engines and equations, where the invisible force we call entropy begins to whisper its quiet rules, shaping everything from the ticking of clocks to the burning of stars. From here, the story opens into a quieter question, one that sits halfway between imagination and evidence. For centuries, we've been taught to think of the universe as solid, spacious, three-dimensional. We can walk forward, turn left, step upward. The distances between stars, the sweep of galaxies, all feel like part of a grand, continuous volume. Yet when physicists look closely enough, they begin to see something unsettling. The world might not be as thick as it seems. It could be thinner, almost like a mirage painted on the surface of something deeper. The idea seems impossible at first. How could everything we touch, every mountain and planet and person, exist as a kind of projection? And yet in the late 20th century, the clues began to whisper in that direction. They came not from mystics or philosophers, but from the practical language of thermodynamics, the study of heat, work, and the restless flow of energy. When you heat a pot of water, energy moves, molecules jostle, spread, and rearrange. That simple motion obeys a set of laws so dependable that engineers have built entire civilizations upon them. But hidden inside those same laws are hints about information, about how nature counts, stores, and forgets. It was in the mathematics of steam engines that the earliest signs of the universe's strange thinness began to appear. To follow that thread, imagine an engine. In the 1820s, a young French engineer named Sadi Carnot was obsessed with building the perfect one. He watched locomotives groan and spark their way across Europe and wondered why they never seemed fully efficient. Some of the heat from the firebox always escaped. Some of the motion was always lost. He didn't have the language of atoms yet, but he sensed there was a deeper rule, a limit written into nature itself. Carnot described an ideal cycle, heat flowing from a hot reservoir to a cold one, pushing a piston in the process. No matter how carefully he arranged it, some energy always slipped away. He had discovered the outline of what would later be called the second law of thermodynamics, the rule that in every exchange some order dissolves into disorder. That loss, tiny but universal, became one of the most important ideas in all of science. Rudolf Clausius later gave it a name, entropy. In simple terms, entropy measures how much of a system's energy is unavailable for useful work, how much has drifted into randomness. If you pour cream into coffee and stir, you can't unmix it again. The molecules remember the blending, not the separation. Entropy is that memory, the direction that gives time its arrow. But entropy is more than just a story about waste. It is a story about information. Each time heat spreads, the universe gains a new record of what happened. It cannot go backward, because the information that would reverse it has been lost to the dance of countless particles. This realization led later scientists to suspect that every process, every flicker of heat, carries a hidden account book. Somewhere, reality keeps score. When we reach far beyond engines to black holes, those cosmic furnaces that swallow light itself, the same accounting reappears. The laws of thermodynamics still apply. The surface of a black hole behaves like a hot object, radiating slowly, counting its internal states the way an engine counts its strokes. But there, the numbers begin to tell a stranger story. The amount of information a black hole can contain does not depend on its volume, as intuition suggests, but on the size of its surface. Imagine that. A star collapses into a sphere so dense that not even light can escape. Yet all the information about what fell in, every atom, every field, every pattern, is somehow stored on its skin. One bit of information for each tiny patch of surface no larger than the square of the smallest conceivable length. What physicists call the Planck area. We don't need to say the numbers. They are unimaginably small. What matters is the revelation. Information in our universe seems to care more about area than about volume. That is the first hint of the holographic principle. The notion that reality might be like a book whose entire story is printed on its cover. Think of a hologram etched on a thin sheet of film. Shine a beam of light on it, and a three-dimensional image blooms into view. The depth you see is not real depth. It is the way your eyes interpret interference patterns written flat on the surface. Every angle, every shadow, every curve of the image exists within that flatness. The illusion of thickness arises only when light passes through. Now replace the beam of light with the laws of physics themselves. When they interact with the information written on the universe's distant boundary, the result might be what we call three-dimensional reality. In that view, we're not creatures moving through space. We're part of a luminous pattern being projected from a cosmic surface we can never reach. This doesn't mean reality is fake or digital. It means that the deepest description of it might live on a boundary, the way the rules of a game can be printed on a box while the players move freely inside. The particles, stars, and galaxies could be the living enactment of a two-dimensional script. It's an elegant idea, and also an unsettling one. If true, it means that space, distance, even the idea of inside and outside may be emergent, illusions built from information. We are used to thinking of the universe as vast, but in this picture, everything we know is contained in a kind of cosmic skin, thinner than thought, yet infinitely rich. To hold that image in your mind, imagine a soap bubble floating in sunlight. Its surface shimmers with colour, and though it seems delicate, it contains the entire story of the air trapped within. The bubble's edge defines everything. Without the surface, there is no inside. Perhaps the universe is like that. A bubble of information where the surface is reality itself, and what we call depth is only the way light dances across it. This is not an ending, but a beginning. To understand how such a thin cosmos could behave so richly, we must follow the thread back through the human mind, to the people who first noticed that entropy, information, and geometry might belong to the same family. Our trail leads us to a small desk in post-Napoleonic France, where a young engineer's disappointment with steam would quietly ignite the physics of everything. In the next step of our journey, the story of the cosmos becomes the story of a man sitting beside a furnace. Before equations began whispering about the edge of reality, there was fire, simple, practical fire, burning beneath iron pistons and steaming metal giants. It was here, among the heat and the hiss of the early industrial world, that one of the most profound ideas in science quietly began. The year was 1824. France was still trembling from the fall of Napoleon, its empire turned to ashes, its streets filled with the echo of lost ambition. Among the new generation born into that uncertainty was a quiet young engineer named Sadi Carnot. His father had been a famous mathematician and general, but Sadi himself would not command armies. His battlefield was the engine room, a place of gears, pressure, and possibility. Carnot worked in an age obsessed with progress. Steam powered everything. Trains shrieking through the countryside, factories alive with motion, ships crossing oceans on columns of smoke. But even in this age of miracles, something bothered him. Every engine, no matter how finely made, wasted energy. Heat slipped away through pipes and into the air, lost forever. Perfection seemed close, but never reached. He began to wonder if the loss was not a flaw of design, but a law of nature. If perhaps, hidden behind the iron and the fire, there was a limit that no machine could cross, a ceiling written into the mathematics of the universe itself. And so, in a small room in Paris, Carnot began to imagine the perfect engine. He pictured heat as a river flowing from hot to cold, from firebox to piston, from furnace to exhaust. If that river could be harnessed perfectly, every drop of heat might be turned into motion. But something stopped it. Even in thought experiments, the flow of heat never completed the circle. Some energy always remained behind, unreachable, unusable. He described the best possible cycle any engine could achieve, a loop of heating and cooling that defined the very border between what was possible and what was not. This was the birth of thermodynamics, the study of how energy moves and changes form. Carnot didn't know about atoms or molecules yet, but he sensed that heat was not a mysterious substance. It was motion, a restless vibration running through matter. And motion, he realized, always spreads. The perfect engine was an illusion because nature itself leans towards sharing. Heat cannot be kept locked in one corner. It diffuses like scent in the air or ink in water until everything finds balance. That balance, the state where energy is evenly spread and no useful difference remains, became the cornerstone of what physicists later called the second law of thermodynamics. To understand it gently, imagine you're sitting in a quiet kitchen. A cup of tea steams on the table. If you leave it untouched, the warmth will eventually fade. The air around you grows slightly warmer, the tea cooler. What was once a concentrated little pocket of energy spreads outward, smoothing itself into the world. You can never make it flow back on its own. That one-way slide from hot to cold, from order to disorder, is entropy in motion. Carnot couldn't have known that his study of pistons and boilers would one day echo in the equations of stars and galaxies. But the law he uncovered, that energy has a preferred direction, applies everywhere. From a cooling cup of tea to the slow dimming of suns, the universe follows the same path. It moves toward balance. Decades after Carnot's death, other minds began to refine his vision. Rudolf Clausius gave the phenomenon its name, entropy. He described it as a measure of how energy becomes unavailable for work. In modern words, it's the part of energy that slips through our fingers, the part that still exists but can no longer be used to drive a wheel or light a lamp. Clausius also saw what that meant for time itself. Since entropy never decreases, the universe is always moving forward, never backward. Time's arrow is carved into the flow of heat. A few years later, an Austrian scientist named Ludwig Boltzmann would take the idea further. He realized that entropy isn't just about heat, it's about possibility. The more ways a system can rearrange itself while still looking roughly the same, the higher its entropy. He explained it through simple logic. Suppose your kitchen is spotless, every dish put away, every surface shining. There's only one precise arrangement that gives you that perfection. But if it's messy, there are countless ways it can be messy. The number of possible microstates, as Boltzmann called them, explodes. The universe, in its quiet impartiality, always drifts toward the state with the most possibilities, the state of higher entropy. It's not that nature prefers chaos. It simply follows the rules of counting. There are far more ways for things to be disordered than for them to be ordered, so over time, that's where everything drifts. It's probability disguised as inevitability. The elegance of this idea is that it connects the everyday with the cosmic. The same rule that cools your tea also drives the death of stars. It determines why smoke spreads, why memories fade, and perhaps even why we grow older. Everything that changes leaves behind a trail of lost order. Entropy is the shadow every event casts across time. But Carnot's insight contains something else, a quiet optimism. If perfection is impossible, then imperfection is universal. Every spark, every breath, every moment of warmth happens because energy seeks to spread. The same law that forbids eternal motion also allows motion to exist at all. Without that imbalance, nothing would move, burn, or live. In that way, Carnot didn't just discover a limitation, he discovered a rhythm. The universe breathes through difference, hot and cold, light and dark, energy and rest. The second law is not a sentence of decay, but a song of equilibrium slowly finding its refrain. If you listen closely, you can almost hear it in the hum of an old radiator or the sigh of cooling metal. The sound of energy evening itself out, one vibration at a time. And so, from one man's fascination with engines, we inherited the first universal rule of change. Yet the deeper meaning of entropy, its relationship to information, to time, and to the geometry of reality, was still waiting to be uncovered. If we follow the thread a little further, we will see how these ideas, born from the heat of steam, grew into the mathematics that describes not just engines but everything, from atoms to galaxies, from black holes to the edge of the universe itself. As we drift further into the story, the rhythm of heat and motion begins to sound more familiar, almost human. The law that Sadi Carnot first sensed, that energy always slips, that perfection can never be captured, was no longer just about engines. It had begun to reveal something deeper, something that touched not only metal and fire, but the very logic of existence. By the middle of the 19th century, the industrial world had grown louder, and so had science. In smoky lecture halls and laboratories filled with brass instruments and glass tubes, physicists tried to refine the rules Carnot had glimpsed. One of them was Rudolf Clausius, a German scientist who loved clarity above all else. Clausius didn't invent the idea of energy, but he gave it structure. He realized that the heat flowing through an engine or a living cell must obey a balance, just as coins in a ledger obey arithmetic. He wrote, in soft German, prose, that energy cannot be created or destroyed. It can only change form. What we now call the first law of thermodynamics was born from that simple sentence, yet it was his second statement that changed everything. In any natural process, the universe's entropy, its measure of unusable energy, always increases. Entropy, he said, is the bookkeeping of the universe's disorder. It measures how evenly energy has been spread, how much potential for structure has already dissolved into chaos. You could picture it like ink spreading in water. Each swirl adds complexity, yet takes you closer to uniformity. Clausius didn't use that imagery, but he might have smiled at it, for he believed that behind every act of motion was a quiet surrender. But entropy, as Clausius defined it, was still an abstraction. It worked on paper, but no one quite knew what it meant in the world of atoms. At the time, atoms themselves were still a debated idea. Some scientists believed they were mere mathematical fictions, convenient symbols rather than real things. Then came Ludwig Boltzmann, a man whose mind burned brighter than his age could easily contain. Boltzmann was born in Vienna in 1844, when physics was beginning to bridge the visible and the invisible. To him, atoms were not abstractions. They were tiny, restless citizens of nature, each with its own position, velocity, and story. If Clausius gave entropy its name, Boltzmann gave it its soul. He imagined a gas as a ballroom full of countless invisible dancers. Each molecule moved at its own tempo, bumping, spinning, colliding. No one could ever track them all, but in their wildness, Boltzmann found order. He realized that what we call heat, the smooth, continuous thing we feel on our skin, is really the average motion of an unimaginable number of these tiny dancers. Temperature, then, is just their excitement level. When the music quickens, the dancers move faster. When it slows, they rest. Entropy, Boltzmann saw, is not a mystical force but a statistical truth. It tells us how many ways the dancers can rearrange themselves while the room still feels the same. He wrote an equation for it, a simple link between entropy and the number of possible microscopic arrangements of particles. The formula itself can stay unspoken. What matters is its meaning. The more ways the tiny parts can be organised without changing the overall scene, the higher the entropy. Imagine, he said, a tidy kitchen, every plate stacked, every spoon aligned. There's only one way to achieve that kind of order, but the moment you start cooking, the possibilities explode. There are thousands of ways for dishes to be misplaced, crumbs to scatter, towels to wrinkle. Disorder, statistically, is simply more likely. That realization turned the second law of thermodynamics from a mysterious rule into something inevitable. The universe doesn't choose chaos because it loves mess. It chooses it because there are far more paths that lead there. Entropy is the arithmetic of chance. In this way, Boltzmann transformed heat from a metaphor into a map of probabilities. Every gas, every flame, every living breath was part of a cosmic lottery, each molecule rolling its own dice. When we add up all those rolls, the patterns we see emerge naturally, like music arising from countless instruments tuning at once. It was a triumph of insight, but also a lonely one. Many of Boltzmann's peers rejected his view. They said probability had no place in fundamental science. To them, nature should be exact, deterministic, predictable. But Boltzmann understood something profound, that certainty is a luxury of large numbers. The universe doesn't care about perfect predictability. It only cares about patterns that endure when chaos is averaged out. And so, through the language of statistics, he revealed that order and disorder are not opposites, but partners. Order creates the conditions for disorder to emerge, and disorder allows new forms of order to appear. Stars form from clouds of chaos, and chaos itself is just the spread of too many possibilities to count. Boltzmann's work quietly redefined what it means for something to exist. Every physical system, a flame, a drop of water, even a thought, can be described by the number of microscopic ways it can arrange itself. To exist is to have a range of possible patterns. Entropy is simply the measure of how wide that range can be. It is humbling to realize that the same logic guiding a steam engine also guides the birth of galaxies. Entropy explains why stars burn out, why ice melts, and why the universe itself seems to drift towards stillness. But it also explains why anything happens at all, why energy flows, why matter stirs, why life itself arises from the improbable. Boltzmann never lived to see his ideas universally accepted. He died believing his greatest insight might be forgotten. But today, his equation is carved on his tombstone, not as a cold calculation, but as a testament to the poetry of chance. It says that within every system lies an invisible crowd of possibilities, and entropy is how the universe counts them. When you feel the warmth of sunlight on your skin, you're feeling the same dance Boltzmann described. The average tremor of countless particles exchanging energy, drifting toward balance. And yet, in that drift, there is creativity. The spreading of heat allows life to feed, stars to shine, and minds to think. Entropy, then, is not the enemy of order. It is the pulse of existence itself. From here, our trail begins to shift once more, from heat and engines to information and thought. The same patterns that describe the flow of energy will soon describe the flow of knowledge. And somewhere in that meeting, at the edge between motion and meaning, we'll find the first whisper of how reality remembers itself. Our quiet exploration now turns from steam and metal toward the strange stillness of space. The same laws that guided engines and boilers would in time reveal their reflections among the stars. What began as a study of heat and motion on Earth would one day whisper secrets about the most mysterious objects in the cosmos, black holes. And at the heart of that revelation stood a man who saw science not as a cold pursuit, but as a form of devotion. His name was Jacob Bekenstein. Bekenstein was born in Mexico in 1947 to Polish parents who had fled the storms of war. He grew up in an ordinary neighborhood, in a world that had seen too much destruction, and found solace in order, in the way numbers never lied, and the stars moved with quiet discipline. He would go on to study physics at Princeton, where another young thinker named Stephen Hawking was also beginning to turn his gaze toward the heavens. But while Hawking saw the universe as a puzzle to be solved, Bekenstein saw it as a cathedral to be explored. He believed that studying nature was not an act of defiance against mystery, but an act of worship within it. It's easy to imagine him late at night, bent over his notes, candlelight flickering on the page, tracing the outlines of the unseeable. To him, the universe was not chaos dressed as order. It was a divine design, waiting to be read correctly. And yet, the question he chose to study was as close to cosmic heresy as science allows. He wanted to know what happens to information, the deepest kind of order, when it falls into a black hole. Black holes at first seemed to mock every law of thermodynamics. They were born from Einstein's general relativity, equations so precise they could predict the bending of light itself. When a massive star dies, it collapses under its own gravity, crushing itself into a region so dense that not even light can escape. The boundary around that region is called the event horizon, a one-way gate. Whatever crosses it vanishes from the visible universe. Physicists soon realized how strange this was. If nothing can leave a black hole, then anything that falls in, matter, radiation, even information, appears to be gone forever. But according to quantum theory, information cannot be destroyed. Ever. The universe keeps perfect records, even if we can't read them. So what happens when those records cross the horizon? Bekenstein looked at that question and saw a paradox. He began to wonder if perhaps the answer was hidden on the horizon itself. Black holes, he noted, could be described completely by just 3 numbers: their mass, their electric charge, and their spin. That simplicity led his mentor, the physicist John Wheeler, to call it the no-hair theorem. It was a joke, an elegant way of saying that black holes have no distinguishing features. 2 black holes could be born from completely different stars, yet if their mass, charge, and spin matched, they would be identical. But Bekenstein saw something strange in that: simplicity. If every other object in the universe carries information, a fingerprint of its internal state, then why should black holes be different? Could it be that they too hold information, but only on their surface? He began to suspect that a black hole was not an object of nothingness, but an object of memory, that its surface might act like a cosmic archive. To explore that possibility, he returned to the law of entropy. Every physical system, from a gas to a galaxy, has entropy, a measure of how much information about its internal structure has been blurred away. A black hole, by all logic, should have the highest entropy of all, because it hides everything within. Bekenstein proposed something astonishing, that the entropy of a black hole, its amount of hidden information, is proportional not to its volume, but to the area of its surface. The larger the surface of its event horizon, the more information it can store. To understand why that's profound, imagine writing a message on a balloon. As you blow air into it, the surface expands. Every new bit of area gives you space for more words, more information. The inside grows, but the writing stays on the skin. The black hole, Bekenstein suggested, might be like that. Whatever falls in doesn't vanish. Its information spreads across the horizon, woven into that thin cosmic surface. At the time, this idea seemed outrageous. Entropy was supposed to measure disorder, not geometry. But the numbers worked beautifully. A black hole's surface, when measured in unimaginably tiny squares, each about the size of what physicists call the Planck length, roughly 1.6 times 10 to the negative 35 meters, matched the amount of information it could contain. Every such tiny patch could hold about 1 bit of data, the smallest possible piece of information, like the flicker of a binary code written in light. It was as if the universe itself had been whispering the same rule across every scale. Information clings to surfaces. The smallest quantum of reality, the Planck area, was a natural unit of information, the universe's pixel. Bekenstein's insight was revolutionary, but it raised new problems. If black holes have entropy, they must also have temperature, because entropy and temperature are 2 sides of the same coin. That meant they should emit radiation, losing energy over time. But according to Einstein's theory, nothing could escape a black hole. The contradiction was glaring. Most scientists dismissed the idea. Even Bekenstein's mentor doubted it. But one man decided to test it, armed with equations sharp enough to cut through impossibility, Stephen Hawking. He followed the trail of logic deep into the quantum foam around a black hole's surface and discovered, to his own shock, that Bekenstein had been right. Black holes do emit radiation, faint and cold, but real. It was one of the most astonishing results in modern physics. What began as a debate about thermodynamics had led to the edge of reality itself. Bekenstein had shown that the laws of heat and order, first written in the language of engines, also applied to the fabric of spacetime. The universe, from teacups to collapsing stars, obeyed the same rule. Information can hide, but it cannot disappear. And so, the man who saw science as worship had revealed a strange kind of grace, that even destruction preserves meaning. Every particle swallowed by a black hole remains, in some form, as a whisper upon its surface. The cosmos, it seems, forgets nothing. As we drift further into the darkness, the horizon begins to glow faintly. It's the light that Hawking discovered, the quiet radiation of information returning to the world. In that glow lies the beginning of a new paradox, one that will haunt physics for decades. If black holes can evaporate, where does their information go when they vanish entirely? That mystery will carry us deeper still, into the realm where fire meets mathematics, and where the holographic principle begins to emerge. The place where the edge of the universe starts to look a lot like the surface of a black hole. The trail of clues leads us gently into the next chapter of this quiet mystery, where fire and geometry finally meet. Jacob Bekenstein had opened a door that no one expected to find, the idea that black holes, those silent wells of gravity, might have a temperature and an entropy of their own. The thought was daring enough, but the one who stepped through that door and proved it was real was Stephen Hawking. When Hawking began his work in the early 1970s, black holes were considered perfect prisons. They swallowed light, matter and information alike and offered nothing back. The mathematics said they could never radiate, never lose energy. They were absolute, eternal and cold. Bekenstein's claim that they possessed entropy, that they could, in principle, have temperature, sounded not only unorthodox but contradictory. If entropy measures disorder and temperature measures the ability to radiate, then how could something that allows no escape possess either? Hawking initially set out to disprove him. The story goes that he considered Bekenstein's ideas interesting but flawed. Black holes don't radiate, he said flatly. But science, in its patient way, has a sense of humour. As Hawking dug into the equations, using the subtle machinery of quantum theory near the event horizon, he stumbled upon a miracle. At the edge of a black hole, the very concept of empty space begins to change. Quantum physics tells us that even a vacuum is not truly empty. It flickers with virtual particles that appear and vanish too quickly to be seen. These tiny pairs, a particle and its opposite, born together from the energy of space-time itself, usually annihilate each other instantly. But near the event horizon, something strange happens. One particle can fall in while the other escapes. The one that escapes becomes real, carrying away a minuscule bit of energy from the black hole. Over time, those tiny emissions accumulate into what we now call Hawking radiation. It's not a blazing fire, but a ghostly whisper. Radiation so faint that, for the largest black holes, its temperature would be close to absolute zero. Yet it exists. Hawking had shown that black holes are not eternal. They leak slowly over unimaginable timescales, fading like embers cooling in the cosmic night. This realization reshaped physics. If a black hole could radiate, it meant it could eventually evaporate entirely. And that raised a haunting question. When it disappears, where does all the information it once contained go? If the radiation is purely random, as Hawking's calculations first suggested, then the information about what fell in would be erased forever. That would violate one of the most sacred rules of quantum mechanics, the principle that information once created can never be destroyed. Thus was born the black hole information paradox, a riddle that has haunted physicists ever since. On one side stood quantum mechanics, insisting that the universe keeps perfect books. On the other stood general relativity, declaring that black holes erase their ledgers completely. It was a conflict between two pillars of knowledge, each correct in its own domain, yet seemingly irreconcilable when they met at the horizon. To understand how radical this problem is, imagine burning a book. You could, in principle, collect every puff of smoke, every spark of heat, every atom released into the air, and reconstruct the story it contained, at least in theory. The information isn't lost, it's just rearranged. But if you throw that same book into a black hole, and the black hole then evaporates into featureless radiation, it's as if the story never existed. The universe itself would have forgotten a piece of its own memory. For physicists, that was unbearable. If information can vanish, then cause and effect lose their anchor. The rules of quantum mechanics, the very laws that predict the behavior of atoms and light, would crumble. Hawking himself acknowledged this contradiction, even as his equations insisted on it. For decades, he defended the idea that information is indeed lost in black holes. Others, including Bekenstein, Leonard Susskind and John Preskill, argued that it must be preserved somehow, perhaps encoded in the radiation, or trapped on the surface itself. The debate became legendary, not fierce, but profound, like a long philosophical argument carried out with chalk and patience. Hawking, witty as ever, once made a public bet that black holes destroy information, offering a scientific paper as a prize to whoever could prove him wrong. Years later, he quietly conceded the bet. The more physicists explored quantum gravity, the more evidence seemed to suggest that the universe is a careful accountant after all. The information, they believed, never truly disappears. It's hidden, scrambled beyond recognition, but still there. To think of this visually, imagine a black hole as a mirror, not one that reflects your image, but one that reflects meaning. Anything you throw at it, every particle and photon, leaves a faint impression, a pattern in the curvature of space. The surface becomes a kind of memory, storing the outline of everything it consumes. And as the black hole radiates, that pattern seeps out again, like a secret being whispered back into the universe, bit by bit. The numbers tell a poetic story. The smaller a black hole becomes, the faster it evaporates. For one of stellar size, this process could take longer than the age of the universe, trillions upon trillions of years. But if we imagine it to the end, the final moments would be spectacular. The black hole would grow hotter and brighter as it shrinks, until it releases its last energy in a flash of pure light. Somewhere in that final spark, physicists believe, the information would emerge again, restored, not erased. The cosmos, it seems, keeps no true secrets. It only hides them under layers of transformation. In the softest way, this connects us back to Bekenstein's faith. For him, the universe was a divine text written in symbols of energy and order. Hawking, though more skeptical, ended up revealing something equally spiritual, that even in destruction, meaning endures. A black hole may devour, but it cannot annihilate the story of what it has eaten. It merely translates that story into a new form of light. When you think about it, that's not so different from us. We too absorb, transform and emit. Every thought, every breath, every heartbeat rearranges information, turning experience into heat, memory and motion. We are small, living black holes in our own way, absorbing the world and radiating it back as warmth, words and wonder. So far, our journey has followed the path of heat, from engines and entropy to horizons and radiation. But the next turn is subtler. As we step beyond Hawking's faint light, we begin to see that information itself, the abstract concept that ties order and memory together, may be the foundation of everything. Perhaps matter, energy, and even space are only shadows cast by information. And if that is true, then the universe does not merely exist, it remembers. Our quiet journey now leaves the pull of gravity for something lighter, not in importance, but in texture. We've followed heat as it turned into entropy, and entropy as it transformed into questions of memory. Now, those questions begin to take shape as language. The story moves from fire and stars to the faint scratch of pencil on paper, to a young man sitting at a desk covered in half-empty coffee cups and napkins full of equations. His name was Claude Shannon, and though he never chased galaxies, he ended up discovering a law that connects to them all. It was the middle of the Second World War. At Bell Laboratories in New Jersey, Shannon worked on secret communication systems, ways to send messages securely across great distances. While others worried about machines or wires, he kept asking a different kind of question. What is information itself? What is the quantity that moves when a message travels from one mind to another? Shannon was not a philosopher. He was a mathematician who loved puzzles. He believed that information could be counted like marbles in a jar or cards in a deck. To test that idea, he imagined a game. Suppose you're trying to guess a word letter by letter, like in a round of hangman. At the start, the possibilities are endless. Each guess narrows them down. The fewer possibilities remain, the more information each correct guess gives you. In this simple guessing game lay the foundation of information theory. Shannon realized that uncertainty and information are two sides of the same coin. The more uncertain you are, the more potential information there is to learn. The less uncertain, the less new information you can gain. He turned that idea into a formula, not with strange symbols, but with logic. If a message has many possible outcomes, it carries more information. If it's predictable, it carries less. Information, he said, measures the surprise contained in a message. The word entropy, borrowed from thermodynamics, fit the concept perfectly. Entropy in physics measures how many ways a system can be arranged. In communication, it measures how many ways a message can vary. The resemblance between the two was uncanny. Boltzmann had used entropy to describe how particles arrange themselves in gases. Shannon used it to describe how symbols arrange themselves in language. Heat and meaning suddenly shared a grammar. He didn't claim to solve the mysteries of the universe. He only wanted to make telegraphs more efficient. But his discovery quietly rewired the way physicists thought. Information, it seemed, was not just a property of language or computers. It was a universal currency. It could describe atoms as easily as words. To understand how radical this was, imagine the universe as a vast library. Every atom, every photon, every fluctuation of energy is like a page in that library. The total number of ways those pages can be arranged determines the universe's entropy, or in Shannon's language, its information content. Whether the symbols are letters or particles doesn't matter. The logic is the same. This was the insight that caught the attention of John Archibald Wheeler, the great theoretical physicist who mentored both Feynman and Bekenstein. Wheeler saw in Shannon's equations something deeper than communication. He saw a clue about reality itself. It from bit, he said, meaning perhaps that every particle and field is made from bits of information at its core. It was a poetic phrase, one that carried both precision and mystery. It didn't mean the universe was a computer, but that what we call physical things might be secondary to the information that defines them. Matter could be a story told in binary, the universe, a sentence written in light. When we think of information, we often picture something abstract, data, numbers, text. But in the physics Shannon inspired, information has weight. It has energy. A single bit, the smallest unit, representing a simple yes or no, requires a finite amount of energy to exist, to be stored, to be erased. The process of forgetting, it turns out, also releases heat. Even memory leaves a thermodynamic trace. That connection between thought and heat, between meaning and energy, begins to blur the boundaries between physics and philosophy. It suggests that every process of change, from the turning of gears to the firing of neurons, is at heart a process of information moving from one pattern to another. Picture again the black holes we've been travelling with. In light of Shannon's discovery, they begin to look less like monsters and more like libraries, massive storage devices for cosmic data. Each bit of information that falls in becomes part of their record. If the universe were a computer, black holes would be its most efficient hard drives. The Bekenstein-Hawking relationship, where a black hole's entropy depends on its surface area, fits perfectly with this idea. Every patch of horizon holds the maximum number of bits that physics will allow. Even the human mind fits into this pattern. Our brains, humming quietly under the weight of experience, are information processors. Every sound, every memory, every flicker of imagination is a pattern of energy flowing through a neural network, increasing entropy in one place while creating order in another. The act of thinking, of converting uncertainty into understanding, is thermodynamics wearing the mask of consciousness. There's something soothing about this unity. It tells us that the divide between matter and meaning, between the physical and the mental, may not be as sharp as it seems. Information bridges the two. The same equations that describe how electrons scatter in a wire can describe how words scatter in a sentence. The same logic that governs entropy in a cloud of gas applies to the probabilities inside your thoughts. For the first time, physics had found a language capable of speaking about knowledge itself. Still, information theory didn't stop at philosophy. It also set the limits of communication in a measurable way. Shannon proved that there's a maximum rate at which information can flow through any channel, whether it's a radio signal, a fibre optic cable, or the universe itself. There's always a speed limit for meaning, defined not by distance but by noise. Too much noise, and the message dissolves into uncertainty. Too little, and the channel is wasted. Perhaps the same holds for the cosmos. Between the stars and the void, information is constantly transmitted, through photons, through gravity, through the slow ripples of space-time itself, and like all communication, it must obey the same quiet balance between signal and noise. If we follow that thought to its edge, a remarkable picture appears. The universe might be the ultimate message, unfolding letter by letter, bit by bit. Everything we see, stars, matter, even consciousness, could be the translation of information into physical form. Reality, in this view, is what happens when the cosmos speaks itself aloud. In the soft glow of that idea, the noise of war fades, the hum of telegraphs becomes background music, and the scribbles on Shannon's napkins begin to look like the fingerprints of creation. Information isn't just what flows through machines, it's what gives the universe its voice. And yet, the question remains, how small can this voice become before it dissolves into silence? If information is real, then it must live somewhere, in space, in energy, in the very grain of existence. What happens when we follow it down to the smallest scales, where size itself loses meaning? Our path now narrows toward that frontier, to a man named Max Planck, and to a unit of measurement so tiny that the fabric of space begins to shimmer and blur. If we follow the thread a little further, information begins to shrink, compressing itself until it reaches the smallest scales imaginable. Every pattern, every particle, every whisper of energy has to be stored somewhere, and that somewhere has limits. Those limits were first discovered by a quiet German physicist at the turn of the 20th century, a man named Max Planck. Planck lived in an age of grand certainty. Newton's laws seemed unbreakable. The universe was thought to be infinite and continuous, and space was treated as a smooth, empty stage upon which matter performed. But Planck was not convinced. He sensed that beneath that smoothness, something must break down, that there must be a smallest unit, a graininess to reality, the way even the most perfect fabric reveals threads under a magnifying glass. His search began not with cosmology, but with light. Physicists at the time were puzzled by an old problem called the ultraviolet catastrophe. When they tried to describe how objects glow when heated, their equations predicted that as temperature increased, an infinite amount of energy should be emitted at short wavelengths, which clearly didn't happen. The equations worked beautifully for cool red light, but broke down for the blue and violet. Planck realised the problem wasn't with light itself, but with the way we measured energy. What if, he suggested, energy doesn't flow in a smooth, continuous stream? What if it comes in tiny, discrete packets? Little bundles he called quanta. Each packet carried a precise amount of energy depending on the colour or frequency of the light. That one assumption changed physics forever. It solved the puzzle instantly, but it also cracked open a deeper truth. Nature, at its foundation, may be digital, not analogue. From that idea came Planck's natural units, fundamental scales for time, mass, and length. They weren't invented out of convenience like centimetres or miles, but derived from the constants of nature itself, the speed of light, the strength of gravity, and the smallest unit of quantum action. These constants, when combined, give numbers that mark the frontier of physical meaning. The most famous of these is the Planck length, about 1.6 times 10 to the minus 35 metres. That's a distance so small that if you divided a millimetre into a billion equal pieces, each piece would still be far too large. It's smaller than any particle, smaller than any wave, smaller even than the concepts of here and there. At that scale, space itself stops behaving like space. The familiar geometry of distance and direction begins to dissolve into what some physicists call quantum foam, a restless ocean of uncertainty where the structure of space-time flickers in and out of existence. It is here, at this unimaginably small threshold, that Jacob Bekenstein's insights find their full meaning. When he calculated how much information could fit into a black hole, he discovered that nature seems to count in Planck-sized units. Every patch of surface the size of one Planck area, that is the Planck length squared, can hold exactly one bit of information. The universe, it seems, stores its data in the tiniest pixels imaginable. Think of painting a picture. The finer the brush, the more detail you can add, but eventually you reach a limit where the strokes themselves blur together. At the Planck scale, the cosmos reaches that limit. It can't draw any finer. Each Planck area is like one brush stroke in the grand painting of existence, and together they form the shimmering image we call reality. Bekenstein's discovery also revealed something unexpected. The amount of information that can exist inside any region of space is not proportional to its volume, the amount of space it takes up, but to the area of its boundary. This means that a cube and a sphere of the same size can hold the same maximum information if their surface areas match, regardless of what's inside. The universe, it seems, measures capacity not by what fills the space, but by what outlines it. You can imagine this as a library whose knowledge is stored not on its shelves, but on the walls themselves. Every inch of surface carries meaning. The interior is simply where those meanings unfold. This strange realization is what led physicists to suspect that our three-dimensional world might actually be a projection from a deeper, two-dimensional surface. A cosmic hologram where the boundaries encode the entire interior. Even light itself obeys this law. When a beam of light interacts with matter, it doesn't reveal the interior directly. It reveals the way surfaces reflect and absorb it. The surfaces hold the information. A mirror doesn't just reflect. It records the way the world bends around it, carrying that geometry outward. Likewise, the event horizon of a black hole may be a kind of universal mirror, encoding everything that crosses it in a pattern too subtle for us to read. When we speak of 1 bit per Planck area, it might sound mechanical, but it isn't. It's simply a poetic shorthand for the idea that there is a smallest possible step in nature's language, a smallest possible symbol in the script of the cosmos. Below that, the grammar of space breaks apart. The universe doesn't write in infinitesimal ink, it writes in dots, incredibly tiny, impossibly precise dots, woven into a continuum that feels smooth from far away. And there's something comforting in that. It means that even the infinite has a pattern. The sky above us, the heat beneath our feet, the pulse in our veins, all arise from the same finite alphabet. The smallest bits of information, the Planck-sized brushstrokes, combine to paint galaxies, mountains and minds. When Max Planck first wrote down his strange little numbers, he couldn't have known that they would someday connect to black holes, information theory, and the very architecture of the universe. Yet, in a way, his intuition was simple. Every language needs a smallest syllable, and every melody a smallest note. The Planck length, the Planck time, and the Planck energy are those syllables and notes for the song of existence. At this scale, words like inside and outside lose their meaning. Space becomes a fog of relationships. Geometry melts into probability. And yet, from that haze, the universe we know somehow crystallizes. The smoothness of the world, the continuity we see when we look at our hands or the stars, is a grand illusion built from countless discrete notes of information humming together in perfect harmony. If everything we know truly fits upon a surface, then each of us is part of that great pattern. We are shapes traced on the cosmic membrane, ripples of energy encoded on the universe's quiet skin. And perhaps that's why we find patterns so beautiful, because we are patterns looking back at themselves. As our exploration drifts forward, the next chapter of this story will step from mathematics into light itself, from the abstract counting of information to the shimmering waves that carry it. For in the middle of the 20th century, a scientist named Dennis Gabor discovered something extraordinary. That light, too, can remember. Our quiet journey now turns towards something more familiar, the warmth and shimmer of light. We've spoken of heat, entropy and information, all invisible currents of order and change, but light is different. Light is visible. It paints the world we see. And yet, hidden within its waves lies one of the most poetic discoveries in modern science, that light, like memory, can hold the depth of what it touches. The man who uncovered that secret was Dennis Gabor. Gabor was born in Budapest in 1900, into a world balanced between empires and ideas. He loved tinkering with lenses and circuits, but what fascinated him most was something simple: how light carries information. In the early years of his career, he built devices that captured images with electrons instead of photons. They were predecessors to modern electron microscopes, instruments that would later reveal the hidden architecture of atoms. But in 1947, while working in England after fleeing the rise of fascism in Europe, Gabor began thinking about something far less practical and far more profound. He wondered whether a single flat surface, a piece of film or glass, could store not just the brightness of an image, but the way the light waves themselves move and interfere. A photograph captures intensity, the lighter and darker spots, the shadows frozen in 2 dimensions. But when you look at a mountain range or the curve of someone's face, there's more than light and shadow. There's depth, the subtle way light dances across distance. Gabor asked, could that dance be preserved? To answer, he turned to the wave nature of light. Every beam, every glimmer, can be imagined as a ripple travelling through space. When 2 ripples meet, they overlap, sometimes amplifying each other, sometimes cancelling each other out. This interplay, called interference, is what gives rise to the vivid patterns on soap bubbles and the iridescence of peacock feathers. Gabor realised that if he could record those interference patterns precisely, he could recreate not just an image, but the entire wavefront of light itself. In other words, he could make a memory of light, a record that, when illuminated again, would reassemble the original scene in 3 dimensions. The word he chose for it was holography, from the Greek holos meaning whole, and graphan, to write the whole. Imagine standing in front of a hologram, a thin, transparent plate that looks almost empty until light strikes it at the right angle. Suddenly a 3-dimensional image blooms in the air. Move your head and you see around it as if the object were truly there, but it isn't. The information about its shape, its depth, and even its texture is all encoded in the surface, folded into patterns too fine for the eye to see. A photograph, in contrast, freezes a single moment, flattening the world into brightness and shadow. A hologram remembers how light danced. It remembers the rhythm of the waves, the way they curved, collided, and intertwined. In that sense, a hologram doesn't just capture what something looked like, it captures how it existed in light. Gaba's discovery didn't immediately find its place in the world. The technology of his time wasn't ready for it. Lasers, the perfect sources of coherent light needed to make holograms clear, wouldn't be invented for another decade. But the idea waited patiently, like a seed buried in the soil of physics, until the light it required was finally born. When lasers arrived, holography blossomed. Suddenly, the world could see what Gaba had imagined: floating figures, shimmering landscapes, and 3-dimensional memories made of nothing but light. It was both a scientific breakthrough and a philosophical revelation, because at its heart, holography is a meditation on how much information can be stored on a surface. A single square of film no larger than your hand can contain all the information needed to reconstruct a 3-dimensional world. Even more strangely, if you cut that film in half, each piece still holds the entire image, just from a slightly different angle. The whole is present in every part. Information, it seems, can be distributed in ways that defy intuition. Nothing is truly lost, only folded differently. That realization resonated far beyond optics. In the following decades, physicists studying black holes would find that the universe itself behaves in a similar way. The information about everything inside, every atom, every event, might be stored on the boundary, on a cosmic surface invisible to us. Just as Gaba's hologram encodes a 3-dimensional image on a 2-dimensional sheet, reality itself might be a vast hologram, written not in ink or light, but in the fundamental vibrations of space-time. If you close your eyes, you can almost imagine it. The stars, the galaxies, the gentle curve of your own hand, all projections of deeper information inscribed on the farthest edge of the universe, where space becomes too thin to hold anything more. The light you see, the matter you touch, are the visible ripples of that invisible script. It's humbling and strangely peaceful. Because holography reminds us that presence and absence are not opposites. What seems gone can still exist as pattern. What seems distant can still be connected through interference. Every reflection, every shimmer of light, is a dialogue between being and remembering. When Gaba received the Nobel Prize in 1971, he spoke not about the physics, but about imagination. The future cannot be predicted, he said, but it can be invented. It's easy to think he was talking about technology, but perhaps he also meant perception, that how we choose to see the world invents the world we inhabit. A hologram doesn't trick us. It teaches us that vision is interpretation. Reality, too, might depend on how the universe chooses to read its own light. If a thin sheet of glass can hold an entire world within its folds of interference, how much more might be stored on the invisible surfaces of the cosmos? If every boundary is capable of memory, then every horizon, every line between one thing and another, could be alive with information. As we drift deeper into this idea, from the laboratory's dim green light to the dark edge of black holes, we begin to see the pattern emerging, from the whisper of heat to the shimmer of light, from entropy to information. The next step of our journey will return to those cosmic boundaries, where Dennis Gaba's insight meets Jacob Bekenstein's vision, where surfaces do not just reflect the world, but remember it. From here, the story of light folds gently back into the story of gravity. Dennis Gabor had shown that a single sheet of glass could remember the dance of light, every shimmer, every shadow, written into interference patterns too small to see. But what if nature itself works the same way? What if the surface of the universe is also recording constantly, quietly, without pause? That idea, first imagined in the human mind and then whispered by mathematics, begins here, at the edge of a black hole. In the early 1970s, after Geber's holograms had started to glow in laboratories, Jacob Bekenstein and Stephen Hawking were still untangling the puzzle of black holes and information. Hawking's calculations showed that these cosmic abysses were not eternal. They radiated faintly, giving off energy and, in time, shrinking. But that brought back the oldest question. If a black hole fades away, what happens to everything it swallowed? The more physicists studied the numbers, the stranger the answer became. Every quantity, energy, entropy, information, seemed to depend not on what lay inside the hole, but on its boundary, the event horizon. It was as if the three-dimensional interior were just a shadow of the two-dimensional surface. For every Planck-sized patch of that surface, one bit of information was stored. No more, no less. When the idea first spread through the community, many found it hard to believe. How could an entire world, the atoms, the fields, the very curvature of space inside a black hole, be represented on its outer skin? But the equations refused to yield any other interpretation. The deeper scientists looked, the more it seemed that the horizon itself held the code. To picture it softly, imagine a pane of frosted glass. From one side you can't see through it, it looks opaque. But on its surface lies the faint outline of everything behind it, the shadows of what has passed. If you could learn to read those shadows, every detail would return. That, Bekenstein suggested, is what the event horizon might be, a cosmic sheet of frosted glass, preserving the impressions of everything that ever touched it. This idea bridged the world of black holes with Gaber's world of light. In both, the same miracle occurs, a three-dimensional reality encoded perfectly on a two-dimensional surface. Nothing truly vanishes, it only folds itself into pattern. And just as shining a beam of light through a hologram reconstructs the original image, perhaps the universe itself shines with the information once hidden on those horizons. To understand how astonishing this is, recall that black holes were once thought to be simple, just regions defined by mass, spin, and charge. Now they looked like libraries, with every page etched in geometry rather than ink. Every collision, every falling atom, every ray of light that ever crossed the horizon left its mark. The surface was not a blank wall, it was memory. Some physicists began to suspect that this might not just apply to black holes. If the universe obeys the same rules everywhere, perhaps every boundary in space behaves this way. Every horizon, every shell of light that separates one region from another. Information might always live on surfaces. Space itself might be a grand hologram, its depths projected from the boundaries that enclose it. It's a dizzying thought, yet also a soothing one, because it means the universe keeps no secrets from itself. Even when information seems lost, a star collapsing, a thought fading, a moment gone, the pattern remains somewhere, carved into the surface of reality. It may never be retrieved, but it is never truly erased. You can feel the poetry of it. Stand by a window at night, and you'll see your own reflection mingling with the dark outside. The glass holds both images, the light of your room and the faint gleam of distant stars. That thin surface becomes a meeting place of two worlds, just like the event horizon between space and gravity. Surfaces remember, they collect echoes. They are the boundaries where the universe tells its story. As Hawking's work matured, it suggested a tantalizing resolution to the information paradox. Perhaps the data that falls into a black hole never disappears into the singularity at its center. Instead, it remains on the surface, woven into the subtle quantum fluctuations of the horizon. Over time, as the black hole radiates and shrinks, that information leaks back out in the pattern of the escaping radiation, faint, tangled, but still present. The edge becomes the heart, the surface becomes the storyteller. In later decades, physicists would come to see this principle. the idea that all information within a region can be described by its boundary, as one of the deepest clues to the nature of reality. It links gravity, quantum mechanics, and thermodynamics in a single thread. It whispers that the universe might be far simpler and far stranger than we ever imagined. When you run your fingers across a page, you feel raised ink. When you watch the sea, you see its rippled surface but not the depth below. Maybe that's how the cosmos works too. The true complexity of existence might lie not in hidden interiors, but in the quiet textures of its boundaries. Reality, then, could be the ultimate surface, endlessly detailed, endlessly rich, recording everything that ever was. If so, the universe doesn't just exist, it remembers, and we too are part of that memory. Patterns written on the surface of space-time, flickering in and out of the great hologram. Our bodies, our thoughts, even our dreams are temporary configurations of information, rising and dissolving in the same ocean of pattern. When we fade, the imprint remains, however faint, in the vast interference pattern of being. In this vision, death and loss take on a different meaning. What disappears in form may persist in information. What ends in one shape may continue in another, encoded in the endless fabric of light and space. Perhaps that's why starlight from ancient suns still reaches us. A reminder that nothing truly leaves the story. As we drift onward, the surface grows wider. The logic that began with black holes begins to stretch toward the universe itself. In the next step of our journey, the idea will leap from singularities to the cosmos as a whole, carried forward by a handful of daring physicists who asked a simple question. If every black hole is a hologram, could the entire universe be one too? The trail of light that began with Gaber's holograms and Bekenstein's black holes now stretches into the open air of imagination. The year's the early 1990s. The Cold War is ending. Computers are beginning to hum on every desk, and two physicists, Gerard 't Hooft in the Netherlands and Leonard Susskind in California, are about to take a breathtaking step. They will suggest that the entire universe may be holographic, that every atom, every galaxy, every heartbeat could be written upon a distant surface, like reflections on the skin of a soap bubble. To reach this idea, they began not with mysticism, but with frustration. For decades, physicists had struggled to unite two great frameworks: Einstein's theory of gravity, which describes the grand curves of space-time, and quantum mechanics, which governs the jittering realm of the very small. Each worked perfectly within its own domain, yet when brought together near black holes, or the earliest moments of the Big Bang, they produced contradictions, infinities that defied sense. The two languages of nature could not speak to each other. 't Hooft, a man of quiet precision, decided to look at the problem from the boundary instead of the centre. He noticed that whenever gravity is involved, the number of things you can fit inside a region, the number of possible states it can have, always seems limited by the area of its surface, not its volume. This mirrored Bekenstein's and Hawking's black hole findings, but he suspected it might be universal. Maybe every region of space, not just those swallowed by gravity, obeys this strange rule. He proposed what he called the holographic principle. Imagine, he said, a world described by 3 dimensions, but whose true description lives on a 2-dimensional boundary surrounding it. The interior would be like the image inside a hologram, a projection arising from information stored on the surface. Gravity, the bending of space itself, could simply be the way that surface information arranges and rearranges. Susskind, famous for his restless energy and warm humour, saw the beauty in this immediately. To him, the idea wasn't just mathematics, it was a rescue. It offered a way to reconcile black holes with quantum mechanics, to preserve information rather than lose it. If the information about what falls into a black hole is stored on its surface, then no paradox remains. The universe keeps perfect records as quantum theory demands. Susskind elaborated on 't Hooft's intuition with imagery that was almost childlike in its clarity. Think of a soap bubble, he said. Its surface glistens, alive with colour. The pattern on that thin skin determines the shape of the bubble itself. Gravity, in this view, is not something acting within the bubble, but a manifestation of how the surface bends and flexes. The cosmos might be built the same way, a three-dimensional illusion born from a two-dimensional script. To visualize this gently, imagine standing before a giant aquarium. Fish swim inside, plants sway, light refracts through water. From your vantage point, it all feels deep. But suppose everything you see, the motion, the colours, even the sense of depth, is being projected from a thin panel of glass at the front. The fish are still real. They move, interact, and live their little aquatic lives. But their world is the unfolding of patterns written on that transparent sheet. That, in essence, is what the holographic principle proposes for reality itself. When Susskind published his work in 1995, he titled it "The World as a Hologram." The phrase caught on, spreading beyond academia into popular imagination. But in physics circles, it was far from a metaphor. It was a serious proposal about how information behaves in gravitational systems, and it had a quiet elegance that appealed to scientists who had spent decades wrestling with equations too unwieldy to tame. Here was a principle that could explain why black holes possess entropy proportional to their surface area, and why the universe, even at its larger scales, might follow the same rule. The principle doesn't say that our world is a projection in the cinematic sense. No invisible projector casting our lives onto a cosmic screen. Rather, it says that the deepest description of the universe may reside in fewer dimensions than we experience. What we perceive as depth, volume, and distance could emerge from the interplay of data stored elsewhere, like the way a three-dimensional scene arises from patterns on a holographic film. The beauty of this idea lies in its economy. Nature, it seems, never uses more than it must. If the universe can describe itself perfectly, using only 2 dimensions of fundamental information, why insist on 3? Perhaps what we call space is just how our senses interpret a vast, intricate web of relationships. The universe might not be a thing filling a void, but a conversation between its boundaries. For Hooft and Susskind, this was not mysticism, it was clarity. The equation suggested that gravity itself could emerge from information, that spacetime might be the geometry of entropy. Every patch of space, every region of curvature, would be the visible shadow of hidden data on some underlying surface. The implications were staggering. If this were true, then the cosmos could be thought of as an enormous network of correlations, with each point connected to every other. Distance would be an illusion, a side effect of information being arranged in certain ways. What we call locality, the sense that things occupy specific places, might be no more fundamental than the perspective of an observer looking at a hologram from one angle rather than another. Still, for all its elegance, the holographic principle was, at that time, a conjecture, a piece of poetic mathematics without experimental proof. Yet even as it remained theoretical, it began to reshape the language of physics. Words like surface, boundary, and information replaced substance, inside, and matter. Scientists began to imagine the universe not as a stage but as a code, a system of relationships. The world became less about things and more about patterns. To stand back from all this is to feel a quiet sense of symmetry. From Carnot's engines to Boltzmann's probabilities, from Bekenstein's horizons to Shannon's bits, each chapter of our story has turned entropy into a bridge between the tangible and the abstract. De Hooft and Susskind took that bridge and extended it across the entire cosmos. They suggested that the universe might be readable from its edges, that the vastness above us is the unfolding of a hidden script too grand for our eyes but perfectly consistent in its design. Perhaps that is why the holographic idea resonates beyond physics. It carries the same soft humility that whispers through all great discoveries, that what we see is only a reflection of something deeper, that every surface conceals a story, and that the universe, in all its shimmering detail, might be the most intricate mirror ever imagined. As we drift further into this dream of surfaces and shadows, a quiet figure appears on the horizon of our story. A young Argentinian theorist with a piece of chalk in his hand, ready to draw the doorway that will link two worlds. His name is Juan Maldacena, and what he's about to discover will turn the holographic principle from an elegant metaphor into a concrete bridge, one that connects gravity, quantum theory, and the very shape of space itself. The path now carries us toward a quiet office at the Institute for Advanced Study in Princeton, sometime in the late 1990s. The room is ordinary, chalk dust on a desk, a pot of coffee, cooling beside a window, afternoon light slanting across papers scattered with equations. And at that desk sits a young Argentinian physicist named Juan Maldacena, unaware that the lines he's about to draw will become one of the most beautiful bridges in modern science. Maldacena was searching for a way to make sense of two worlds that refused to meet: the smooth geometry of Einstein's gravity and the restless chaos of quantum mechanics. For decades, physicists had tried to stitch them together, like tailors working from different sides of the same cosmic fabric. Each side looked perfect in its own pattern, but when the edges met, they refused to align. The resulting picture was torn by contradictions, infinities, paradoxes, impossible symmetries. Maldacena approached this riddle with unusual calm. He was not looking for a new theory to replace the old ones. He was looking for a reflection, a way to see one system mirrored in another, so that the impossible could become visible from a different angle. His insight came from string theory, the framework that imagines all particles not as points, but as tiny vibrating loops of energy. These loops could, in theory, exist in more than the familiar 3 dimensions, sometimes up to 10 or 11, depending on the mathematics. It sounds extravagant, but it offered something precious, a structure that might include both quantum mechanics and gravity under one roof. Yet string theory had a problem. It was almost impossible to solve. Its equations were too complex, its space too vast. Maldacena wondered if perhaps the answer was not to tackle the equations head-on, but to look at them from their edge. He began with a type of mathematical universe called anti-de Sitter space, or ADS for short. Imagine a universe that curves inward like the surface of a saddle, a place where gravity pulls everything toward the center and the edges stretch toward infinity. In such a space, light rays can leave the center, travel outward, and eventually circle back. Nothing truly escapes. Now imagine that the boundary of that space, this infinite edge, hosts a completely different kind of physics, a world without gravity, described instead by quantum fields interacting on a flat surface. What Maldacena proposed was almost shocking in its simplicity. These two worlds, one with gravity and one without, might actually be the same thing. The theory came to be known as AD-CFT, short for anti-de Sitter, conformal field theory correspondence. It means that the physics of gravity in a 5-dimensional curved universe is exactly equivalent to the physics of quantum fields in a 4-dimensional world on its boundary. 2 descriptions, 2 languages, yet they tell the same story. To picture this softly, think of a snow globe. Inside, tiny figures stand beneath swirling flakes, a little world curving in on itself. But everything that happens inside could, in principle, be described by patterns written on the glass surface, the boundary that separates the snow from the air beyond. The two are not copies, but reflections. One contains gravity, the other does not. One is the interior, the other is the code that defines it. What made this discovery astonishing was its precision. It wasn't just a poetic metaphor, it was mathematically exact. Every vibration of a string in the 5-dimensional world had a counterpart vibration on the 4-dimensional boundary. Every gravitational ripple corresponded to a field interaction. It was as if Maldacena had found a Rosetta Stone linking 2 completely different languages of nature, showing that each could translate the other perfectly. For physicists, it was like opening a window into a hidden symmetry. The unsolvable equations of quantum gravity suddenly became solvable. Not directly, but through their mirror version on the boundary. Problems that seemed impossible inside could be rephrased and answered at the edge. The riddle had solved itself when read from the outside in. The correspondence also gave new depth to the holographic principle proposed by 't Hooft and Susskind. It was no longer an abstract idea about how surfaces might encode interiors. It was a working example, a universe that actually does it. The world inside the ad space and the world on its boundary were not two different realities, but one single, self-consistent entity seen from different viewpoints. This revelation rippled outward through theoretical physics like the faint echo of a gong. Suddenly, researchers saw connections everywhere, between black holes and quantum entanglement, between gravity and thermodynamics, between spacetime itself and the flow of information. If two worlds could mirror each other so precisely, then perhaps the fabric of reality was woven from relationships rather than from things. Even outside of physics, the idea carried a quiet resonance. It suggested that boundaries are not limits but bridges, that what happens at the edge defines what lies within. Every horizon, every interface between one system and another may hold the key to understanding the whole. When asked about his discovery, Maldacena often speaks with modesty. He does not claim to have found the final theory of everything. He sees ad CFT as a clue, a demonstration that the universe might be self-dual, able to describe itself from the inside and the outside at once. It's a mathematical truth that feels almost philosophical, that wholeness and surface, depth and outline are merely two ways of telling the same story. If you listen closely to the rhythm of this discovery, it feels familiar. It echoes the same harmony we've traced since Carnot and Clausius, the idea that opposites, when understood deeply enough, begin to merge. Heat and work, order and disorder, surface and volume, gravity and information, each pair, once thought to be in conflict, turns out to be complementary. In AdCFT, that balance becomes literal. The interior and the boundary reflect each other perfectly, like two mirrors facing across a quiet room, and somewhere between them, in the infinite regress of reflections, the meaning of the universe begins to appear, not as an answer, but as an endless conversation between what is seen and what is hidden. Maldacena's chalkboard, dusted with equations, might seem far removed from the night sky. Yet in that room, the geometry of everything shimmered for a moment, caught between thought and truth. A young man had drawn a doorway between two worlds, and behind it lay the possibility that space-time itself is not fundamental, but emergent, arising from the entanglement of information spread across the universe's skin. And so, our path widens once more. From a single engineer studying heat to a century of thinkers tracing its echoes through gravity, entropy and light, we've arrived at a breathtaking possibility that all of existence might be a holographic song, each note a reflection of something deeper. But even the most elegant ideas must face the test of reality. In the next stage of our quiet exploration, we'll step into the places where the holographic dream begins to meet its limits, where experiments, skepticism, and the texture of our own expanding universe begin to question how far this beautiful symmetry can reach. As we drift further into the story, the harmony we've built begins to meet its dissonance. The holographic principle, with all its beauty, has so far lived in a universe that curves inward, the world of anti-de Sitter space, the kind one Maldacena drew in chalk. In that world, gravity is like a bowl that gathers everything back toward the centre. Light that escapes from the middle eventually returns. Nothing is lost forever. It is a perfect stage for balance, reflection, and mathematical symmetry. But the universe we actually inhabit is nothing like that. It does not curve inward. It stretches outward. Our cosmos expands with gentle acceleration, its galaxies drifting apart faster and faster, carried by a mysterious dark energy that pushes rather than pulls. This scientists call de Sitter space, a universe that curves outward, like a hill rather than a bowl. And in this outward-leaning reality, the holographic dream begins to tremble. The difference between the two might sound subtle, but it changes everything. In anti-de Sitter space, there is a clear boundary, a well-defined edge at infinity where information can be written, stored, and retrieved. The mathematics is neat, almost musical. In de Sitter space, as the kind we live in, there is no such fixed boundary. Everything expands, and the edges recede faster than light can travel. The horizon of what we can see keeps slipping away, like a mirage that runs from your gaze. This poses a question as delicate as it is profound. If holography needs a surface to store information, and our universe has no static surface, then where does the cosmic code reside? Where is the great mirror upon which reality writes itself? Physicists have spent decades trying to answer that, each offering their own fragment of the puzzle. Some suggest that the boundary of our observable universe, the sphere beyond which light has not yet reached us, might serve as the storage surface. Others think the horizon of time itself, the ultimate limit of what can ever be observed, carries the imprint of everything that happens. But unlike the clean reflective walls of Maldacena's ADS universe, the horizon of our world flickers and shifts. It is not a static recording device. It is a living, breathing frontier, moving outward with every second that passes. To imagine it softly, picture standing on a shore that constantly recedes as you walk toward it. You can never touch the line where sea and sky meet. It defines your world, yet you can never reach it. That is what cosmologists face when they look for the holographic boundary of our universe, a horizon that exists by retreating. Some scientists like Eva Silverstein and Tom Banks have tried to build a version of holography that works for de Sitter space. They imagine that perhaps the information is not stored at a distant edge, but scattered throughout, woven into the very expansion itself, like a melody carried not by one instrument, but by the whole orchestra at once. Others think the answer may lie in quantum entanglement, the invisible threads connecting distant parts of space. Maybe the horizon is not a physical surface at all, but a network of relationships, an abstract boundary made of shared information. There is a quiet irony here. The more we try to pin down the universe, the more it slips through our fingers. Just when we think we've found the perfect equation, reality reminds us that it doesn't sit still long enough to be measured. The expansion of space is both gift and riddle. It gives us room to exist, but denies us the certainty of knowing the whole. And yet, even in this uncertainty, there's poetry. The outward curve of the cosmos, the endless growth of its horizon, means that creation is not finished. The universe is still writing itself, line by line, into new space. If the holographic principle is true, then that script is expanding too, an ever-widening page of cosmic text, unfolding faster than any reader could follow. Some physicists believe that this very imperfection might hold the next great insight. If holography in anti-de Sitter space was the first chapter, perhaps the de Sitter version will be the sequel, one that explains not only the structure of space, but also the arrow of time, the reason we remember the past and not the future. After all, in an expanding universe, information does not just sit on surfaces. It moves, drifts, and diffuses, carried outward by the tide of creation. Entropy increases, space stretches, and memory itself becomes part of the expansion. You can feel it in something as simple as a breath. When you exhale, your warmth diffuses into the air, spreading outward until it vanishes into the atmosphere. The information about that warmth, its exact pattern, its tiny molecular signature, still exists somewhere, but it's diluted beyond recovery. The universe may work the same way on a grand scale. It remembers everything, but not always clearly. Its archives are written not in ink, but in expansion. For theorists like Susskind and Maldacena, the de Sitter dilemma remains both a frustration and a challenge. The mathematics that sing so smoothly in the inward curved world of ADS becomes dissonant in our outward curved one. Some call it the cosmic mismatch, a reminder that our universe, with its relentless stretching, refuses to fit neatly into the frames we build for it. Yet that refusal may be a sign of life, a clue that the universe's most beautiful truths are still unfinished. It's possible that the cosmic hologram, if it exists, is not etched on some faraway wall, but constantly rewritten on the horizon that expands with us. Every second adds new letters to the script, and every galaxy that drifts beyond view takes its words with it, leaving the text forever incomplete. The universe, then, might be less like a perfect film already projected, and more like a story still being told, one whose ending keeps retreating just beyond our reach. If you look up at the night sky, you can sense this tension. The stars you see are memories, light that began its journey millions or billions of years ago. You are seeing the past, not the present. The farther you look, the older the memory becomes, until you approach the cosmic horizon itself, where the universe fades into its own beginning. That fading, that unreachable edge, may be the closest thing to the boundary we've been searching for. Not a solid wall, but a limit of knowledge, a place where the visible world dissolves into potential. And perhaps that's enough. The beauty of the holographic idea was never its precision alone, but its humility, the way it teaches us that reality may be simpler than it seems, yet infinitely more mysterious. In a universe that expands without end, maybe the ultimate memory is not carved on a surface at all. Maybe it's woven into the act of expansion itself. Every new inch of space, every new heartbeat of time, a continuation of the same cosmic thought. As we drift forward, the horizon still recedes, beckoning us with its quiet glow. Ahead lie the experiments that seek to test this idea, to listen for the faintest static of the holographic pattern, the noise that might reveal the universe's hidden grain. The next step in our journey leads us there, to the laboratories on Earth, where scientists have built machines sensitive enough to hear the whispers of space-time itself. Our journey now leaves the world of equations and enters the realm of instruments, places where the human hand and imagination meet in steel, glass, and light. For all its elegance, the holographic idea remains for now a theory written in chalk. But scientists are nothing if not persistent listeners. If reality truly has a hidden grain, if space itself has texture, tiny ripples or pixels of information smaller than any atom, then perhaps, just perhaps, we can hear it. That's what a few daring teams have tried to do. The idea is simple, at least in spirit. If space-time is not infinitely smooth, then at some unimaginably small scale, there should be a kind of background hiss, a faint jitter in the measurements of distance. Just as sound on a vinyl record carries the static of the grooves beneath the music, space-time might carry its own subtle noise, the echo of the holographic pattern. To catch that whisper, scientists have built exquisitely sensitive instruments, stretching across long tunnels lined with mirrors and lasers. The most famous of these, at the Fermi National Accelerator Laboratory near Chicago, was called the holometer, a name that combines hologram and interferometer. Picture it, 2 tunnels, each about 40 meters long, lying side by side like twin arms of light. In each, a laser beam splits into 2, bounces off mirrors at the ends, and reunites at the starting point. If the lengths of the tunnels ever change, even by the tiniest amount, the returning beams will shift in phase, creating ripples of brightness and darkness. These changes can reveal motion smaller than the width of a single atom. Normally, such interferometers are used to detect gravitational waves, like those built for the LIGO experiment that heard the collision of black holes. But the holometer had a different goal. Its designers, led by physicist Craig Hogan, weren't listening for waves passing through space. They were listening for the tremble of space itself. If space-time were made of discrete bits of information, like pixels on a screen, then its smallest vibrations might create a correlated noise, a synchronized flicker between the two laser arms. For years, Hogan and his colleagues tuned their instruments, fighting against the hum of the earth, the drift of temperature, and the smallest quiver of passing trucks. The noise of the world had to be peeled away, layer by layer, until only the potential noise of the universe remained. The sensitivity of the holometer was almost absurd, capable of detecting motion on the order of a billionth of a meter. And yet, after all the listening, the results were silence. No measurable holographic jitter, no universal hiss. Space, as far as the holometer could tell, was smooth, eerily, perfectly smooth. But silence in science is never a failure. It's a kind of answer, one that narrows the field of possibility. If space-time is granular, its grains must be even smaller than we can yet detect. The universe keeps its secret, but not unkindly. It simply whispers more softly than our current ears can hear. Around the same time, other experiments were attempting to probe the same mystery in different ways. Some looked at the behavior of gamma rays from distant galaxies. If space-time were grainy, high-energy photons might travel at slightly different speeds, arriving in our telescopes out of sync. But again, the cosmos seemed perfectly precise. No delay, no drift, no sign of irregularity. Others searched for patterns in the cosmic microwave background. The faint afterglow of the Big Bang stretched thin across the sky. If the universe were a hologram, its early light might carry the telltale fingerprints of interference, like the rings on a holographic plate. Some studies even hinted at anomalies, tiny fluctuations that looked almost too regular, too patterned to be random. But none were decisive. And so, the mystery endures. A theory elegant enough to seduce the mind, yet elusive enough to defy confirmation. Still, there's something quietly moving about these efforts. Imagine the patience it takes to build a machine that can measure distances smaller than anything we can imagine, to line up mirrors with such care that the difference between perfection and failure is less than the width of a proton. The scientists who work on these instruments often describe their experience not as frustration, but as reverence. The act of listening for the universe's smallest voice feels almost spiritual, a modern echo of those who once stared at stars, hoping to hear the music of the spheres. And perhaps in a way they do. Because even when the holometer fell silent, it still told us something about our place in the cosmos. It reminded us that reality, whatever its texture, is astonishingly stable. You can stretch 2 laser arms across the Earth and watch the light return for days, months, years, and it will still return in rhythm. The universe may be stranger than we know, but it is also faithful. There is another kind of experiment, quieter and slower, that happens every night when we look up. Every photon that reaches our eyes from a distant star has crossed billions of years and unthinkable distances. If space-time were a hologram, if it were pixelated or jittery, those photons would have blurred, scattered, or lost coherence long ago. Yet they arrive crisp, carrying the colour and memory of their origin. The night sky itself may be the oldest, simplest hologram test there is, and so far, the image remains clear. Of course, none of this disproves the idea. It only deepens the mystery. Holography was never meant to be a simple claim. It is a question wrapped in elegance. The silence of experiments might be the universe's way of saying, not yet. We may need new tools, new languages, or even new forms of perception to hear the faint hiss of information humming beneath reality. And if that day comes, it won't diminish the wonder. The search itself is part of the story. The long patience of minds who build instruments fine enough to listen to nothing, hoping to hear everything. The hum of lasers in the dark, the vibration of air in underground tunnels, the quiet footsteps of night shift scientists checking mirrors. These are our modern lullabies, sung to the universe in the hope that it will sing back. As we drift beyond these laboratories, one question still hovers gently in the air. What if the silence itself is the signal? What if the perfect smoothness of space-time, the unbroken rhythm of light, is the hologram's way of revealing that the illusion is flawless? From here, our quiet path turns toward reflection, not in mirrors or instruments, but in the mind itself. The next part of our journey will explore what happens when theories grow too beautiful to confirm, when elegance becomes both a triumph and a trap, and science must decide whether to believe its own poetry. Our quiet exploration now turns inward, to the realm where equations meet imagination. For all the elegance of the holographic universe, the smooth geometry, the perfect mirrors, the harmony between gravity and quantum mechanics, there remains a soft unease. Even the most breathtaking theories can become traps, woven as much from longing as from logic. Science, at its heart, is a human story. It is not just about numbers and experiments, it is also about beauty, the strange sense of rightness we feel when a pattern fits, when a formula hums like a well-tuned chord. Physicists often speak of elegance, the way artists speak of proportion. But sometimes, beauty can seduce us. It can make us believe in an idea long before we have proof. String theory, the vast mathematical structure that inspired holography, is a perfect example. It was born from a dream of unity, a single framework that could describe every force, every particle, every vibration of reality. In this vision, the universe is built not from point-like atoms, but from tiny vibrating strings of energy, each playing its own note in a cosmic symphony. The vibration of one string becomes an electron, another becomes a photon, and the different harmonies form the laws of physics themselves. It is a beautiful dream. But beauty, as science has learned, is not the same as truth. When researchers tried to test string theory, they found it retreated into invisibility. The vibrations of those tiny strings occur at scales so small, far beyond the Planck length, that no experiment can reach them. The equations require extra dimensions curled up too tightly to observe, hidden like folds in the fabric of space-time. Even the Large Hadron Collider, the most powerful machine ever built, saw no trace of the supersymmetric particles that string theory predicted. Yet, rather than collapse under this silence, the theory adapted. Its equations allowed so many variations, so many possible universes, that almost anything could be true somewhere. Instead of one tidy cosmos, string theory offered a multiverse, perhaps 10 to the power of 500 possible worlds, each with its own laws. In one, gravity might be stronger, in another, stars might never form. Ours, then, would simply be one thread in an infinite tapestry. It was a revelation and a surrender at once. A theory that explains everything can also explain nothing, because it forbids no possibilities. The beauty that once promised clarity had dissolved into abundance. Even Leonard Susskind, one of string theory's champions, admitted that perhaps nature is messier than the symmetry we hope for, that the universe might be less like a perfect crystal and more like a wild garden, blooming in every direction. Still, it's hard not to admire the courage behind these ideas. To sit in front of a blank chalkboard and imagine 10 dimensions humming beyond sight requires faith of a special kind. Not religious faith, but creative faith, the belief that reality must have order, even if it hides it well. Theoretical physics, in this sense, becomes a kind of poetry written in the alphabet of mathematics. It asks not only what exists, but what could exist if beauty were law, and perhaps that is where its true value lies. Even if string theory, holography, or any of their descendants turn out to be wrong, they have already expanded our imagination of what real can mean. They have shown that space might not be a stage, but a story, that time might not be a river, but a rhythm, that matter itself might be the music, not the instrument. Still, some scientists grow restless with untestable elegance. They remind us that physics was built not on beauty, but on stubborn evidence. Galileo's telescope, Newton's prism, Curie's radioactive salts, all spoke through experiment, not hope. The holographic principle, for all its grace, still waits for its telescope, its prism, its salt. This tension between the dreamers and the doubters is not a flaw but a rhythm of science itself. Every great advance begins as speculation. Every law begins as a rumour. Theories must first seduce the mind before they can be judged by reality. The danger lies only when the seduction becomes faith, when we begin to defend a theory not because it has earned our trust, but because it has stolen our hearts. And yet, how could it be otherwise? Humans are creatures of pattern. We crave harmony, whether in art or in physics. When we look at the night sky, we don't just see stars, we see constellations. When we read equations, we don't just see symbols, we see stories. It's our nature to find design in the dark. In that sense, perhaps the beautiful trap of theories is not really a trap at all. It's a necessary part of our journey, the way curiosity leads us beyond what we can measure. Without that hunger for beauty, science might never have left the ground. We needed people who could look at steam engines and see the laws of thermodynamics. People who could look at black holes and see the language of information. People who could look at a chalkboard and see the universe reflected back. There's a soft humility in realizing that nature doesn't owe us elegance. The cosmos is under no obligation to be simple or pleasing. Its truth may be tangled, asymmetrical, and unfinished, but that's all right. Perhaps the real beauty of science lies not in its answers, but in its willingness to keep asking, to keep sketching possibilities even when the chalk breaks, to keep listening even when the universe is quiet. And sometimes, when theory and evidence finally meet, as they did when Hawking radiation emerged from equations once dismissed as fantasy, the beauty becomes real again, transformed from metaphor into law. We remember that the same patience that drives speculation also drives discovery. The two are mirrors of each other, imagination reaching forward, experiment pulling back, and in between them, truth flickering like light between waves. As we drift toward the next horizon of our story, that flicker becomes our guide. Ahead lies a new vision of the universe, not as a static projection, but as something alive and self-organizing, where space and time themselves might arise from the interweaving of information. It is here, at the frontier where gravity meets quantum entanglement, that the holographic idea finds new life, and where the universe begins to remember itself. Our story now begins to fold inward, toward a realization that feels both mathematical and strangely human, that the universe might not be built from matter or energy alone, but from connection itself. The very space between things may not be a background, but a web, a living network of relationships that gives birth to distance, shape, and gravity. This idea, born from the quiet frontier of quantum theory, is as delicate as spider silk and as daring as any dream before it. Imagine a tapestry. Every thread runs through many others, crossing, looping, binding. Pull one thread, and the entire pattern shifts. The threads don't merely sit on a surface, they are the surface. This, in a soft way, is how physicists are beginning to picture space-time itself. The threads are not fibres of matter or light, but invisible links of information, what we call quantum entanglement. In ordinary life, when we separate two objects, we expect them to act independently. If you place two candles on opposite sides of a room, the flicker of one cannot affect the flame of the other. But at the quantum scale, things behave differently. Two particles that have interacted become deeply connected, sharing a single description even after they are pulled apart. If one changes its state, the other seems to know instantly no matter how far it has drifted. Einstein called it spooky action at a distance, a phrase that sounds like a magician's trick but is now a measured fact of nature. Entanglement doesn't mean messages travel faster than light. Instead, it suggests that the two particles are not truly separate. They are part of one extended system, one invisible whole. Distance, in this sense, is not a wall between them. It's a kind of illusion born from the web they share. Now imagine this idea multiplied across the universe. Not just two particles, but countless trillions of them, all connected in subtle ways, their states interdependent, their existence defined by shared information. What we call space may simply be the pattern that emerges from that web. In this view, space is not a container for things, it is the geometry of connection itself. A physicist once proposed a haunting experiment of the imagination. Suppose you could take two regions of space, each described by its own quantum information. Now slowly cut the connections, erase the entanglement between them. The more you sever, the less they remain part of the same universe. At a certain point, the space between them literally disappears. They drift apart not because of movement, but because connection itself has unraveled. In other words, when the universe forgets how two places are related, those places cease to share space. It's a thought both strange and comforting. Space, as we experience it, might be nothing more than the memory of how things are linked. Gravity, then, could be an echo of information trying to remain connected. When matter bends space, perhaps it's not mass pulling on fabric, but relationships rearranging their balance. Entropy, information, and geometry, three languages of reality, begin to merge into one. To picture this more gently, think of an old woven rug. Its threads are frayed, its edges worn, but the pattern is still visible. Each knot depends on the others for meaning. The red only looks bright beside the blue. The curves exist only because of the tension that holds them together. Tear a piece away, and the entire design shifts, yet somehow endures. That endurance, that quiet persistence of pattern, might be the truest definition of space. This idea is sometimes called emergent spacetime, the notion that space itself is not fundamental, but a product of deeper, invisible rules. Just as temperature arises from the random motions of countless molecules, space might arise from the collective relationships among quantum systems. It's not that we live inside space, it's that space lives inside the information connecting us. If that sounds abstract, consider how naturally it fits our experience. When you think of someone far away, a friend, a loved one, they may be distant on a map, yet close in feeling. The emotional bond erases geography. In physics, entanglement is something similar, but woven into the fabric of existence itself. Two electrons that once touched carry a trace of each other forever. The universe remembers every meeting, every exchange in the delicate architecture of its quantum code. From this perspective, the cosmos is less like a machine and more like an organism, a living memory of interactions. The galaxies that drift apart are still connected, not by force, but by shared information from the moment they were born. Every star, every particle is a note in the same symphony of entanglement, humming quietly through the void. We used to think of space as emptiness, a silent stage where matter moves. Now we begin to suspect the opposite. Matter may be the punctuation, but space is the language. Its grammar is the rule of correlation, its syntax the structure of information. Pull one particle from its neighbour, and the rest of reality shifts to compensate, ensuring that the whole still makes sense. It's difficult to imagine, and yet something about it feels intuitively right, as if the universe had been whispering it all along. We see hints of it everywhere, in the way a magnetic field knows the shape of its source, in the way a melody feels incomplete if one note is removed, in the way a memory depends on context to stay whole. Every system, every pattern, is a web of relationships maintaining its own coherence. And so, when we talk about the edge of the universe, we may not be talking about a boundary in space, but about the limits of connection, the outer edge of what is still entangled. Beyond that, perhaps, lies nothing to see because there is nothing related enough to be seen. Maybe the universe doesn't live in space at all. Maybe space lives in the universe's memory. And if memory is what gives rise to distance and closeness, then we, our thoughts, our stories, our small acts of remembering, are part of the same cosmic fabric. Every connection we make, every act of empathy, every shared thought is another thread woven into the grand tapestry. When you look at someone and feel understood, you are, in a way, reenacting the same principle that shapes galaxies, the emergence of unity from entanglement. And that is perhaps the gentlest truth of all, that the universe is not held together by force but by relationships. What binds space is not strength, but connection. As our exploration continues, that idea deepens. If space-time truly emerges from information, then the laws of gravity, the very curvature of the cosmos, might be shadows cast by the movement of data. Every fold in space could be a paragraph in a story the universe writes about itself. And so, in the next quiet step of our journey, we'll read that story, the story of a universe that remembers itself. From here, the story grows stiller, like the hush that follows the last note of a song. We have wandered through heat and gravity, through light and memory, and arrived at a thought that feels almost alive, that the universe might not simply exist, but remember itself. Every star, every particle, every thread of space could be part of an unfolding act of recollection, a vast, self-sustaining memory. To understand this softly, imagine that space-time is not an object but a language, one written by the universe to describe itself. Each fold of space, each curve of gravity could be a line of that script. When matter gathers, when energy flows, the writing changes. The cosmos is forever editing its own autobiography. Scientists exploring this idea speak of emergent gravity, the notion that what we call the pull of mass, the bending of space-time, may not be a fundamental force at all, but the result of information arranging itself. Gravity could be the geometry of understanding, the way the universe keeps its different parts in agreement about what reality is. It's a breathtaking suggestion, but flows naturally from what we've already seen. Entanglement connects the smallest scales of existence. Holography tells us that boundaries encode the whole. Information theory shows that meaning is woven into every change. Emergent gravity simply ties the threads together. Space, time, energy, and memory all as facets of the same quiet order. One physicist once put it beautifully. He said that gravity may arise from entropic forces, that is, from the tendency of information to spread, to balance, to find equilibrium. In that sense, every motion from the fall of an apple to the orbit of a planet could be the universe's way of seeking the most harmonious arrangement of information. You don't need to picture equations or symbols. Just imagine a flock of birds adjusting their flight, each responding to the others until the pattern stabilizes into grace. Gravity might be the same, the harmony of information taking shape. If this is true, then space itself is not a stage, but a process, a relationship unfolding between bits of information. The curvature of space-time would be the shadow of that relationship, the visible trace of the invisible balance beneath. Every fold of space, every ripple of gravity is a paragraph written by the universe about what it has already known. This brings us to one of the most haunting insights of modern physics, that black holes, those seemingly simple spheres of gravity, might behave like perfect memory devices. They are not just dead ends of matter, they are archives. The information that falls in is not lost but rewritten on their surfaces, stored in patterns that preserve the structure of the whole. In recent years, scientists have discovered that these patterns behave like quantum error-correcting codes, the same logic that keeps your digital photos from being corrupted on a hard drive, but far more profound. Think of a black hole not as a monster, but as a librarian. It accepts every book thrown into it, every atom, every photon, and locks it safely away in a code that can never be erased. The titles and words might be scrambled, but the information remains. Even as the black hole evaporates, the story within it escapes, one bit at a time, carried out in the gentle hum of radiation. The universe, it seems, refuses to forget itself, and if that logic holds, it may not apply only to black holes. Perhaps every region of space works the same way, preserving the memory of its interactions in subtle, distributed codes. Every movement of energy would write a new line in spacetime's memory, and those lines would never fully fade. They would blend, overlap and evolve, but the underlying record would persist. A cosmic diary written in the geometry of being. To feel this, imagine walking through a forest after rain. The air still holds the scent of wet earth, even though the storm has passed. The ground remembers each drop, not in sound or sight, but in the freshness that lingers. The universe may carry the same kind of fragrance, a memory of every motion, every exchange, every flicker of creation that has ever occurred. Some physicists now speak of holographic entanglement, the idea that the shape of space, its curves, its distances, its flow, can be described entirely by the pattern of entanglement among its parts. The more two regions of space are entangled, the closer they appear. The less connected they are, the farther apart they seem. Space itself is therefore nothing but a map of relationships. In that sense, where something is depends entirely on how deeply it is connected to everything else. You could say that the cosmos is a mind that thinks in geometry. Its thoughts are relationships. Its memory is the shape of space-time. And we, being made of the same materials and governed by the same principles, are miniature versions of that same remembering. Our brains are networks of connection, and our thoughts arise from the pattern of those connections, just as space arises from the pattern of entanglement in the universe. Maybe that's why consciousness feels familiar when we talk about it in cosmic terms. The act of remembering, the sense of I am, may not be so different from the universe recognizing its own structure. The same physics that keeps stars in orbit might keep our memories intact. Both are manifestations of information seeking coherence. In this way, memory, physics, and being may be three words for the same quiet act of remembering. There's something humbling in that thought. It suggests that existence is not a series of separate objects, but one vast continuity of memory, an unbroken stream in which every moment folds into the next. The Big Bang, the birth of stars, the pulse of life, the flicker of thought, all different ways of saying the same thing. The universe remembers. When you close your eyes and recall a face or a voice, you are doing what the cosmos does on a grand scale. You are drawing connections between stored patterns of information, bringing the past into the present, reweaving the fabric of meaning. In that sense, you're not simply in the universe, you are the universe, remembering itself in miniature. Perhaps that is what the long journey of physics has been leading toward. Not the conquest of mystery, but its acceptance as something intimate. The equations, the theories, the grand experiments all point to a simple whisper. The cosmos and consciousness are reflections of one another. Both are made of memory, both arise from connection, both persist through change. And so, as our exploration drifts toward its final horizon, the idea of the holographic universe becomes something more than a theory. It becomes a metaphor for belonging. We're not observers standing at the edge of the world. We are patterns in its story, echoes in its memory, filaments of its thought. To exist is to be remembered. By the universe, by time, by one another. And as the story continues, we begin to approach that final question. If everything we are is written somewhere on the cosmic surface, what does it mean to live within a universe that has no true edge at all? What does it mean to be a shadow made of light, shining softly at the border between reality and reflection? That is where our journey leads next, into the quiet frontier where edges fade and the universe begins to look like a thought dreaming of itself. As we drift further, the story circles gently back to its beginning. to that old question of edges, of where one thing ends and another begins. For centuries, people have looked into the night sky and wondered if there is a border to it all, a rim beyond which nothing waits. The holographic idea, strange and beautiful, answers with a whisper. Perhaps there is no edge at all, only a surface that folds everything within it. To understand what that means, we might return for a moment to the world of imagination, where we first began. In the quiet terror of H.P. Lovecraft's stories, explorers peered too far into the unknown and glimpsed geometries that their minds could not hold. In those tales, the abyss was something monstrous, a revelation that drove people mad, but today, through the lens of physics, that same abyss feels softer, less like a threat and more like a mirror. For the modern scientist, the unknown is not a demon hiding in darkness. It is a silence waiting to be understood. What Lovecraft called madness, we might now call humility, the recognition that our minds were built for the small, and yet we reach for the infinite anyway. The holographic principle gives this yearning a new shape. It says that everything we see, the stars, the galaxies, even ourselves, might be the shadows of information written on a vast cosmic boundary. To be a shadow, though, is not to be unreal. It is to belong to light. A shadow is form only because light touches it. It carries both presence and absence at once. And so do we. If the holographic idea is true, then we are all reflections, patterns cast by a deeper reality. Not illusions, but impressions. The solidity of your hand, the warmth of a cup, the echo of a heartbeat, all could be projections of something more fundamental, encoded on a surface so distant we can never reach it. Yet, that surface is not elsewhere. It includes us. The boundary and the interior are the same story seen from two perspectives. You could think of it as the difference between a map and the land it depicts. On paper, mountains and rivers are drawn in 2 dimensions, but they carry the full shape of the world. The holographic principle suggests that our universe might work the same way, that the grand 3-dimensional world around us is the living map of a higher order of information. For a moment, that idea can feel disorienting. If everything we touch is a projection, then what are we really? But the more you dwell on it, the gentler it becomes. Because even if we are shadows, we are not random ones. We are precise, intricate, self-aware shadows, shapes of light sculpted by the cosmos to reflect itself. And to be made of light's memory is no less real than to be made of stone. In fact, this notion has a quiet grace that fits beautifully with what we know from physics. Light has always been the messenger of truth. It carries the information of the universe across billions of years, connecting the first spark of creation to our eyes tonight. Every shadow it casts, every reflection, every pattern of brightness tells the story of something that once was. The holographic universe, then, might be the final expression of this truth, that the light itself is what makes reality visible, and that we are its traces. To see this as peace, rather than fear, consider how much comfort there is in belonging to light. A shadow cannot exist without it, and a shadow cannot lose itself. It is always tethered to its source. If we are the shadows on the boundary of reality, then we are also the proof that the source exists. Each of us, every particle, every moment, is a small confirmation that the universe shines. The philosophers of old would have loved this. Plato once imagined people in a cave watching the world's reflections on the wall, mistaking shadows for reality. But the holographic vision inverts the metaphor. Our shadows are not mistakes. They are the real expression of something deeper. The wall of the cave is not an illusion, but the memory of the light beyond. In this way, the ancient and the modern meet, myth and math shaking hands across time. The fear of the abyss becomes reverence. The geometry once thought to hide monsters now reveals meaning. Where Lovecraft saw chaos, we might see connection. Where he imagined indifferent darkness, we find a cosmos rich with care. one that keeps every trace of what it has ever been, folding it gently into the pattern of itself. If you step outside on a clear night and look up, you're seeing more than starlight. You're seeing the record of time, the outermost layer of reality glowing with memory. Each photon carries a story of birth, of motion, of transformation. The light of a galaxy 10 billion years away touches your eyes in this instant. In that moment, you and the galaxy are part of the same equation, the same act of remembering. You are the witness, and you are also part of the record. Perhaps edges, then, exist only in perception. We feel them because our senses must end somewhere, but the universe itself might not have such limits. Its boundary could be infinite and intimate at once, a horizon that surrounds us and lives within us simultaneously. Just as the surface of a sphere has no edge but still contains everything, the cosmos might have no outside at all, only a continuous curve of light and information that folds upon itself. And what, then, is our place in this endless pattern? Maybe we are both explorers and reflections, beings who reach outward while carrying the inward imprint of the same light. Every question we ask, every experiment we build, every dream we dare to form is the universe looking at itself from another angle. We are the shadows that wonder what casts us, but shadows too have purpose. They give form to the light. They create contrast, shape, and story. They allow the brightness to be seen. To be a shadow, then, is not to be small. It is to participate in illumination. As we move toward the closing horizon of our journey, we begin to see that the edge of the universe may not be a place at all. It may be a way of seeing, a boundary between knowing and mystery, between light and its reflection. And the more we look for the edge, the more it recedes, not because it isn't there, but because it lives within every act of perception. The horizon, it seems, is always where we are standing, and beyond it, the light continues. And so, we arrive at the softest part of the journey, the horizon itself. Not a wall, not a border, but a place where thought fades into wonder, and where science turns back towards silence. The holographic idea has led us through centuries of curiosity, from steam engines and entropy, to black holes, to the shimmering equations that might weave space from memory. Now, at the farthest edge of what we can know, we look around and realize that perhaps there was never an edge to reach. The search itself was the horizon all along. It's easy to forget that science and awe were once the same thing. The Victorian dreamers who imagined higher dimensions, the astronomers who traced faint starlight through glass lenses, the mystics who spoke of infinite mirrors, they were all reaching for the same quiet truth. That reality is more than it seems, and that understanding it is another way of loving it. When we look at the holographic principle today, it still carries that blend of rigour and reverence. The math is sharp, the logic unforgiving, yet the image it paints is tender. A universe that keeps no secrets from itself. A cosmos where nothing is ever truly lost. Every moment, every motion, recorded somewhere on a boundary that is both infinite and intimate. A surface that holds the whole. If you picture it softly, the holographic universe is not a simulation or a trick. It's a kind of poetry written in light. The three-dimensional world around you, the hum of the city at night, the weight of your own heartbeat, could be the unfolding of a deeper order, one that uses information the way an artist uses colour. Reality, then, is a painting that keeps painting itself. And in that image, there's no sharp divide between observer and observed. You're not outside the story, looking in. You're a paragraph within it. A sentence that only makes sense when read as part of the whole. The atoms in your hands once drifted through stars. The light in your eyes has crossed cosmic distances. The breath you draw now is stitched into the same fabric that curves space-time around galaxies. You are not watching the universe, you are how it watches itself. If the holographic idea holds any moral, it might be this. Edges are illusions of perspective. We draw them because our senses need endings, frames to hold what would otherwise feel too vast. But the universe, as far as we can tell, draws no such lines. Its horizon moves with us, always just beyond reach, like the line between sea and sky that keeps retreating as we walk. And maybe that's the point. The horizon isn't meant to be crossed. It's meant to remind us that there is always more. When you look at the night sky, you're already looking at the past. Light that began its journey long before you existed. Some of it will never reach us. It will be stretched beyond our view as the universe expands. And yet, those invisible photons still exist, still carry the story of their origin. The cosmos remembers everything, even what we cannot see. That memory, that persistence, is what gives the universe its gentle dignity. There's something deeply human in that. We too are made of memory, not just in our minds, but in our atoms, our instincts, our histories. The iron in your blood was forged in the collapse of an ancient star. The calcium in your bones once flowed in the seas of a newborn Earth. You carry the record of everything that came before, written in the quiet language of matter. You are, in every sense, holographic, a complete reflection of the cosmos contained in miniature. The Victorian scientists who dreamed of hidden dimensions would have loved this symmetry. They imagined stairways to higher worlds, unseen planes of existence shimmering beside our own. In their way, they were right. The higher dimensions turned out not to be mystical heavens, but the invisible scaffolding of information that gives our universe shape. We have climbed those stairs, not with our bodies, but with our understanding. And what we found at the top was not another world, but the realization that this one is already infinite. Even the old fears of edges, of meaninglessness, of cosmic isolation, fade in this light. For if everything is connected through information, if space itself is born from relationships, then nothing is ever truly alone. Every atom in your body is entangled with the rest of the cosmos. Every heartbeat sends a ripple through the web of being. Existence, in its deepest sense, is participation. You're part of the pattern that keeps reality coherent. Perhaps that's what it means to say the universe is a hologram. Not that it is an illusion, but that it is wholeness disguised as multiplicity. Every piece contains the whole, and the whole reflects itself in every piece. Each of us is a surface that remembers the totality of what is. Every thought, every kindness, every act of attention contributes to the unfolding script. And so, when we speak of the edge of the universe, we're really speaking of our own longing, that instinct to reach, to understand, to belong. The universe has no edge, but we do, and those edges are what make us explorers. They are what give shape to our curiosity, to our need for stories like this one. In the end, maybe we never needed to reach the edge at all. The search, the act of looking outward, was the horizon. The moment you wonder, you've already arrived at the boundary between the known and the mysterious. Every question extends that horizon a little farther, and every answer draws it back, until you find yourself standing where you began, still curious, still listening, still part of the conversation between light and shadow. If the universe is a story written on its own surface, then you, listening now, are part of that script, a note in the quiet song of everything. And whether your eyes are still open or beginning to close, whether your thoughts are bright or already fading into dreams, remember, the light that fills the cosmos is the same light that fills you. You're not on the edge of the universe, you're within it, always, perfectly placed in the story it tells about itself. Rest now, traveller. The horizon isn't going anywhere. It will wait, patient as the stars until you're ready to look again.